Hello. Okay. Hi everyone. So good morning all. So first of all, let me know whether audio and video everything is clear. So first of all, let me know whether audio and video everything is clear. So if it is clear, we will continue here. Is audio and video everything is clear? Okay. Clear? Right. Good morning all. So Fani Krish, Namaste. Sakshi Pradeshi, good morning. Reena Ritula, good morning. Rahul Kumar. So Sakshi Pradeshi, Abhishek, Vishnu Sharma, Rahul Kumar, Abhishek Das. Okay. So everyone, good morning all. So today we are going to do the complete revision of EMT. So remember that it is a revision of EMT, right? Okay. So as we are having within 1 or 2 weeks we are having the examination. Okay. So I will just revise the important topics of EMT. So this session is particularly for EC students here. This session is particularly for EC students, right? So in this session I am going to start from Maxwell's equations, right? We'll start with Maxwell's equations, right? And then we'll end up with antennas here. We'll end up with antennas, right? So from Maxwell's equations to antennas, we will try to revise the important topics of EMT, right? Okay. Right. Okay. So first I am going to start with Maxwell's equations. So what are the Maxwell's equations we are having here? We are having 4 Maxwell's equations. Yes or no? So the first one is nothing but what? Gauss law for electric field. So I'll write the Maxwell's equations both in integral form as well as in differential or point form. So what is the integral form here? So the flux that is leaving any closed surface is equivalent to what? Is equivalent to the charge enclosed by that closed surface. The charge enclosed by that closed surface, or the charge that is enclosed, or the charge that is present within the volume that is enclosed by the closed surface, right? So we can write the same thing as closed surface integral E bar dot dA bar is equivalent to what? Is equivalent to triple integral rho v dv divided by what? Divided by epsilon. So the electric flux that is leaving any closed surface, the electric flux that is leaving any closed surface must be equivalent to what? Must be equivalent to the charge enclosed by that closed surface, right? So the charge enclosed by the closed surface means the charge that is distributed within the volume of the closed surface. So that divided by epsilon, right? So we can write the Gauss law for electric field either in this form, or we can represent either in this form, right? Okay, so here this is also we are going to call it as electric flux, and this is also we are going to call it as electric flux only. But the only difference here is whenever we are defining this electric flux is depending upon what? It is depending upon epsilon. That is, it is depending upon the medium parameter. Whereas whenever we are defining this electric flux, okay, so here it is independent of what? It is independent of epsilon. Independent of epsilon. So we can represent in any manner here the electric flux, right? But here for this electric flux, what are the units here? The units are nothing but what? The units are nothing but coulombs. Yes or no? Okay, so here I forgot to represent here rho v dv. Right. See the units of rho v is nothing but the charge per unit volume, that is coulomb per meter cube. For dv the units are nothing but meter cube. So the units on RHS side is coulomb. Right. Okay. Okay. So for this one the units are nothing but what? Voltmeter. The units are nothing but voltmeter. So how I have written the units here? See for electric field the units are nothing but volt per meter, and for this area the units are nothing but meter square. So this meter will get cancelled. So you are going to get the units as what? Voltmeter. Right. Okay. Okay. So if they ask the electric flux in terms of coulombs, then you have to apply this one. If they ask the electric flux in terms of what? Voltmeter, then you have to consider this as the electric flux. Right. Okay, we can express either in this manner and in this manner. So that's why in books, in some books you will see the equation in this manner, and in some other books they will represent the equation in this manner. So both are correct only. Okay, so they are different just in terms of what? In terms of units. Right. So here the units are nothing but coulombs, and here the units are nothing but voltmeter. Right. Okay. Okay. So this is the first Maxwell's equation. So this is called as Gauss law for electric field. So this is called as what here? Gauss law for electric field. Right. Okay. Okay. So if you represent this in point form or differential form, how we can represent here? So we can represent this in point form as a divergence of d bar is equivalent to what? Is equivalent to rho v. Or we can represent the same thing as what? Divergence of E bar is equivalent to what? Is equivalent to rho v by epsilon. So this is the point form or differential form of Gauss law. So how we are going to get this differential form or point form of Gauss law here? So by applying divergence theorem. Yes or no? By applying divergence theorem to this equation, we can get the point form or differential form of this Gauss law. Right. Okay. Okay. So this is the differential form of Gauss law, and this is the integral form of Gauss law. Next. So the next Maxwell's equation here, the second Maxwell's equation. So that is Gauss law for magnetic fields. So Gauss law for B field. Gauss law for B field. So what is Gauss law for B field here? So it says that the magnetic flux that is leaving any closed surface is always equivalent to what? Is always equivalent to 0. So that is, if you take any closed surface here, if you take any closed surface and if you enclose a magnet, let us say you are considering a magnet. So here this magnet is going to have north pole as well as what? South pole. Right. So whenever it is having north pole and south pole, we know that the field lines are going to leave the north pole and they are going to enter at what? They are going to enter at south pole. Yes or no? So this magnetic field lines will always form the closed loops like this. Right. Okay, so that means whatever the field lines that are leaving from the north pole, all those field lines again they are going to enter at the south pole. So that means the net magnetic flux that is leaving this closed surface will be always equivalent to what? Will be always equivalent to 0. Right. Okay, so always the net magnetic flux that is leaving the closed surface is always equivalent to 0. Why? Means whatever the field lines that are leaving the north pole, so all those field lines again they are going to enter at the south pole. So the net magnetic flux that is leaving this closed surface must be equivalent to what? Must be equivalent to 0. Right? Okay. So that is the Gauss law for B field here. So what it is saying? So the net magnetic flux that is closed surface integral B bar dot dA bar. So this represents the net magnetic flux that is leaving any closed surface. So this is equivalent to what? This is always equivalent to 0. Why? Means magnet will always exist as what? Dipole. Okay, we don't have the magnet as a monopole. That means you don't have only north pole separately and south pole separately. We don't have the magnet which is going to have only north pole and which is going to have only south pole. So magnetic monopoles are not possible. Okay, we have not yet discovered the magnetic monopoles. Right. So since this magnet will always exist as a dipole, so and hence whatever the field lines that are leaving the north pole, they have to enter at the south pole, which means always the net magnetic flux leaving any closed surface must be always equivalent to what? Is equivalent to 0. If you are having only one magnetic monopole here, let us assume we are having this case. Okay, so now in this case, if you enclose this north pole with a closed surface, then what will happen here? So the magnetic field lines, we know that the magnetic field lines are going to leave what? Leave the north pole. So all the magnetic field lines are going to leave the north pole. Okay, so if all the magnetic field lines leave the north pole, then we can say that there exists a net magnetic flux that is leaving this closed surface. Okay, so in this case, the net magnetic flux that is leaving this closed surface is not equivalent to 0. If at all there exists a magnetic monopole. But this situation practically is not at all possible. So whatever the size of the magnet you can take, okay, you can cut into smaller and smaller pieces also, still that smaller piece is going to have both north pole as well as what? South pole. So they will exist always as a dipole. So this monopole is not possible. So up till now we have not discovered any magnetic monopoles. Okay, okay. So which means this case is not at all possible in practice. If at all you have discovered magnetic monopole, then you have to change this Maxwell's equation, right? Okay, but as of now we have not yet discovered any magnetic monopoles, so this situation is not possible. Always this situation is possible, and hence the net magnetic flux that is leaving any closed surface must be always equal to 0. So here they can ask you a question like which of the following Maxwell's equations represents that the magnetic monopole doesn't exist. Okay, if they ask that question, then the answer must be this equation here. So this equation, why we are getting it as equal to 0? Because magnetic monopoles doesn't exist. So that's why we are getting it as equal to 0. Right? If at all magnetic monopole exists, then the flux leaving the closed surface is not equal to 0. Right? Okay. So we are getting this equation because of what? Because of magnetic monopoles. Monopoles doesn't exist. Okay. Now for this equation, if you apply divergence theorem here, we know divergence theorem, that is we can convert the closed surface integral into what? Volume integral, right? Okay, so you can write this as what here? So you can write this as if you apply divergence theorem, okay, what this divergence theorem says here? So closed surface integral some vector field, the flux leaving any closed surface, we can represent it as what? This is equivalent to triple integral divergence of f bar into what? dv. So in this manner we can represent the divergence theorem, right? We can convert the closed surface integral into what? Into volume integral, right? So if you apply the divergence theorem to this LHS side, we can convert this closed surface integral into what? Into volume integral, right? Okay. So if you do that, what you are going to get? You are going to get triple integral divergence of b bar into dv is equivalent to what? Is equivalent to 0. So from here we can write it as divergence of b bar is equivalent to what? Is equivalent to 0, right? Okay, so this is the representation of Gauss law for magnetic field, Gauss law for magnetic field in point form or differential form, right? See, I have already told in my previous lectures this divergence, curl, gradient, all are defined at a point. Okay, okay, so this is called as, that's why it is called as what here, point form or differential form, point form or differential form, right? Okay, of Maxwell's equation. So divergence of B bar is equivalent to what? Is equivalent to 0. So this equation also, it is also nothing but what? We got this equation from this equation only. Okay, so we can say that this equation will also represent what? Will also represent that magnetic monopoles doesn't exist. Since magnetic monopoles doesn't exist, we will get divergence of B bar is always equivalent to what? Is always equivalent to 0. Right? Okay? Okay. So divergence of B bar is always equivalent to 0. So this is also for what? So they can give the Maxwell's equation either in integral form or in differential form, and they may ask you which of the following Maxwell's equation represents that magnetic monopoles doesn't exist. Then your answer must be either this one or this one. So whatever the equation they will give, both are what? Both are correct only. Right? Okay? Okay. Right. Is this clear? Tell me here. So Gauss law for B field. Right. Next. Next we are having another Maxwell's equation. So that is Faraday's law. So that is the circulation of electric field. The circulation of electric field around any closed loop is equivalent to what? Is equivalent to minus double integral dou B bar by dou T dot what? Dot dA bar. Okay, so what actually this equation says here? So the circulation of electric field around any closed loop is equivalent to what? Is equivalent to minus double integral dou B bar by dou T dot dA bar. See here, I can represent this equation in this manner, that is minus of. Okay, so here if you observe the differentiation we are doing with respect to time and the integration we are doing with respect to space, right? So the operation with respect to time and the operation with respect to space, both are what? Both are independent to one another. So which means you can perform any operation first and then you can perform the other operation. That means you can either do first differentiation and then integration, or you can perform first integration and then you can do the differentiation. Okay, any of this you can follow here because both are independent to one another. This differentiation and integration both are independent to one another because here we are doing the differentiation with respect to time, whereas the integration is with respect to what? Space, right? Okay, so the same expression I can write in this manner, that is if I take this dou by dou T outside here, if I take this dou by dou T outside of the integration, I can write it as minus dou by dou T double integral what? Double integral B bar dot dA bar. So this double integral B bar dot dA bar will represent what? Will represent the magnetic flux. Will represent the magnetic flux. Okay, so this dou by dou T will represent what? This dou by dou T will represent time rate of change of magnetic flux, and this minus sign is because of what? This minus sign is because of Lenz's law. This minus sign is because of Lenz's law, right? Okay, okay. So whenever there is a change in magnetic flux, whenever there is a change in magnetic flux with respect to time, then there induces an electric field, or I can say there induces an EMF around the closed loop. See, what do you mean by circulation of electric field around any closed loop here? If you observe, the units for electric field is volt per meter and the units of this DL is nothing but meters. So here this meter will get cancel. So this represents what? This represents the voltage. It represents the voltage that is induced around any closed loop. So that induces a voltage around any closed loop, or I can say that induces an EMF around any closed loop if and only if you have any change in magnetic flux through that loop. Okay, if you take any closed loop like this, okay, so if there is a change in magnetic flux, let us say the magnetic field is penetrating through this loop, right? Okay, so the magnetic flux that is penetrating through this loop, if it varies with respect to time, then there induces an EMF around this closed loop. Okay, so that's what this Faraday's law is going to tell you. See, I'm going through all these Maxwell's equations in a very brief manner, right? Okay, okay, because we have to revise all the topics today, right? Okay, so it is just a revision class here, right? Okay, so if you are having any doubts, you can ask me. You can give your comments in a chat box if you are having any doubts, right? Okay, okay. Right, so whenever there is a change in magnetic flux, then there induces an EMF around a closed loop, right? Okay, or you can say this induced EMF around the closed loop as a circulation of electric field around any closed loop, right? Okay, okay, so this is nothing but Faraday's law. So that is the circulation of electric field around any closed loop is equivalent to minus dou by dou t double integral b bar dot what dot dA bar, right? So generally this b bar dot dA bar double integral will represent it as what? Magnetic flux. So generally we will represent that magnetic flux with phi p, right? Okay, so this is the Faraday's law here. This is Faraday's law, right? Okay, so here this magnetic field, whenever there is a change in magnetic flux with respect to time, it is going to produce an electric field around what? Around the closed loop. So here it is not dA bar, it is dL bar. Okay, okay, right. So the time rate of change of magnetic flux is producing this electric field. So this is what you have to understand here, right? Okay, so next, if you write this in a differential form or point form. So how we can write this in differential form or point form here? So you can apply, so to this LHS side you can apply what? You can apply Stokes theorem. You can apply Stokes theorem. Okay, so what Stokes theorem says here? So we can convert the closed loop line integral into what? Surface integral with respect to what? With the help of Stokes theorem. So that is, if you are having closed loop line integral f bar dot dl bar, so you can convert this into what here? Surface integral, that is double integral curl of what? Curl of f bar dot what? Dot dA bar. So we can convert the closed loop line integral into what? Into surface integral with respect to what? With the help of what? With the help of Stokes theorem, right? Okay, so if you apply the Stokes theorem to this LHS side, so I can write this as what here? Tell me. I can write this equation as how I can write? So I can write this as a double integral curl of what? Curl of E bar dot what? Dot dA bar is equivalent to what? Is equivalent to minus dou by dou t double integral B bar dot dA bar, right? Okay, so on this side the surface integration and on this side the surface integration will get cancelled. So finally you are going to get what? You are going to get curl of E bar is equivalent to what? Is equivalent to minus dou B bar by dou t, minus dou B bar by dou t, or you can write this as since this B bar you can write it as what? Mu into H bar. Okay, so mu is constant with respect to time, so you can take it out of this differential operation. So I can write this as minus mu into what? Minus mu into dou H bar by dou t. So in this manner I can represent. So you can represent either in this manner or in this manner. Okay, so this is the point form or differential form of what? Of Faraday's law. curl of E bar is equivalent to what? Minus dou B bar by dou T, or you can represent it as minus mu into dou H bar by dou T. Okay. Okay. So this is the point form or differential form here. Point form or differential form of what? Of Faraday's law, right? Okay. Okay. Next here. So next, the final Maxwell's equation we are having, so that is Ampere's law. So generally we call it as a modified Ampere's law. So if they ask you the question, who has modified the Ampere's law? Okay, so the credit for the modification of Ampere's law will goes to what? Will goes to Maxwell here. So Maxwell is the hero of our subject, right? Okay, so the prediction of that means the modification of Ampere's law is done by whom? Is done by Maxwell, right? Okay, so what he has done is he has discovered a new current that is associated with the dielectric medium here. So that current we call it as a displacement current. See, we are having two types of current. So one is conduction current and another one is displacement current, right? So this conduction current is the current that is associated with what? That is associated with a conducting medium, right? Okay, and so he has discovered, Maxwell has discovered this displacement current. So this displacement current is associated with what? Is associated with the dielectric medium, okay. So we know only this conduction currents here, okay, so that are associated with the conducting medium. So in a conducting medium we know that free charge carriers are available. So when we apply some potential difference across a conducting element, okay, so this applied voltage, this external applied voltage is going to exert the force on the free charge carriers, and these free charge carriers will start moving in the conducting medium. So which results in what? Which results in the conduction current. Okay, so this conduction current is because of what? Because of flow of free charge carriers inside a conducting medium. Okay, so why they are going to flow in a particular direction? Because we are going to apply some external voltage, okay, across the conducting material. So that external voltage is going to apply a force on these free charge carriers, right? So that's why they are going to flow in a conducting medium. So then we call that current as what here? We call that current as a conduction current, right? So similarly our Maxwell has discovered another current that is associated with what? Associated with a dielectric medium. But in dielectric medium we don't have any free charge carriers. Yes or no? In conducting medium we are going to have free charge carriers. So whenever you apply some electric field or some electrical force on those free charge carriers, right, then that free charge carriers are going to experience this force and they will start moving, yes or no, inside the conducting medium, which results in the conduction currents. But in dielectric medium, if you consider some perfect dielectric medium, right, so in a perfect dielectric medium we don't have any free charge carriers. Okay, then how we are going to get this displacement current? So what is the cause of this displacement current? See, the cause of this displacement current is nothing but the time varying electric field here. The cause for this displacement current is nothing but time varying electric field. Time varying electric field in a dielectric medium. So what is the cause of this displacement current? which is associated with the dielectric medium. So what is causing means a time varying electric field in a dielectric medium. So if you are having a time varying electric field in a dielectric medium, that is going to cause what? That is going to cause this displacement current, right? Okay. So if you are having a static electric field, then it is not going to cause any displacement current in a dielectric medium. Only time varying electric field in a dielectric medium is going to cause this displacement current. You have to keep this point in mind, right? Okay. So we are having two types of currents. One is conduction current, that is associated with the conducting medium, and another currents are nothing but displacement currents, which are associated with the dielectric medium. The cause for this conduction currents is nothing but what? If you apply some electrical force across what? Across a conducting material. Okay, then the free charge carriers that are present in that conducting material is going to experience that electrical force and start moving according to that applied electrical force. So which is going to cause the conduction current in a conducting medium, right? And in a dielectric medium, if you able to produce a time varying electric field in a dielectric medium, that time varying electric field is going to produce what? Is going to produce the displacement current. Okay, so this discovery was done by what year? Was done by Maxwell, right? Okay, so we will see the importance of this discovery. As we proceed, we will understand the importance of this discovery and the importance of Maxwell, right? Okay. So here the circulation of magnetic field, what the modified Ampere's law says here is, so I am writing here modified Ampere's law. So generally in books they won't write it as a modified Ampere's law, so they will simply write it as Ampere's law. Okay, but you have to understand that this is modified Ampere's law. So what is this modified Ampere's law? So it says that the circulation of H field, around any closed loop is equivalent to what? Is equivalent to double integral JC bar dot dA bar plus double integral ZD bar dot what? Dot dA bar. Okay, I will explain here. See, this JC bar dot dA bar represents what? This double integral JC bar dot dA bar represents the conduction current. Okay, see, the units of JC bar is nothing but what? Ampere per meter square, and the units of this dA bar is nothing but meter square. So here this meter square will get cancelled. You are going to get what? Ampere. Okay, so this current is associated with what? Is associated with the conducting medium, right? So Maxwell has discovered another type of current which is called as what? Which is called as a displacement current. This is displacement current. So double integral ZD bar dot dA bar will represent what here? Displacement current. So here this ZD bar, the units of ZD bar is nothing but what? This is the displacement current density. So the units of this one is nothing but ampere per meter square, and the units of dA bar is nothing but meter square. So meter square will get cancelled. So this represents what? This represents the displacement current term. Okay, so if you are having the circulation of magnetic field around any closed loop, what is the cause of this circulation of magnetic field here? What is the source of this circulation of magnetic field? So whenever you are having current, then only you are going to have the magnetic field. So the source of this circulation of magnetic field around any closed loop is nothing but what? Is nothing but current. Yes or no? So that current may be what? That current may be conduction current, and that current may be what? That current may be displacement current. So if you are dealing with purely conducting medium, so in that conducting medium, in a perfect conducting medium, this ID will become equivalent to what? 0. You are going to have only conduction currents, right? Okay, so in a perfect conducting medium, if you are dealing with a perfect conducting medium, so in that medium ID will become equivalent to what? 0. I have already told that this ID is going to associated with what? Only dielectric medium. Okay, so if you are having a perfect conducting medium, so which means it is not having any dielectric nature. So in that case, you don't see any displacement currents in that type of medium. So in that case, you are going to get the circulation of magnetic field. That means the cause of this circulation of magnetic field around any closed loop is caused by what? Is caused by only conduction currents. So similarly, in the same manner, if you consider only a perfect dielectric medium, if you consider a perfect dielectric medium, then this conduction currents will become equivalent to what? 0. Because we know that Jc is equivalent to what? Sigma into E. So if you consider a perfect dielectric medium, this sigma will go to what? This sigma will go to 0. So Jc will become equivalent to 0. So which means in a perfect dielectric medium, this conduction currents are not at all possible. So only what are the currents that are possible here? That is nothing but displacement currents. Okay, so here I will tell what is this ZD bar. So I have already told here the displacement current. What is the cause of this displacement current? A time varying electric field in a dielectric medium. That is the cause for the displacement current, right? Okay, okay. So now see here, what is this ZD bar? So I can write this equation. So that is fourth Maxwell's equation, that is circulation of H field around any closed loop is equivalent to what? Is equivalent to double integral. I can write this as Jc bar plus what? Plus Zd bar dot what? Dot dA bar. Okay, I am combining these two here. If I combine these two, so this is the integration with respect to surface. This is also integration with respect to surface. So if you combine these two integrations, I can write in this manner. So here Jc bar is nothing but what? Is nothing but sigma into E bar. Whereas this Zd bar is nothing but dou d bar by dou t. Okay, here I am not deriving any things here, right? Okay, so because if you go on doing the derivations and all, so we can cover at most 1 or 2 topics, not all the topics of EMT. Okay, okay, I hope you can understand that. So Zd bar is nothing but what? Dou d bar by dou t. So here this dou d bar by dou t, where this d bar is nothing but what? Epsilon into what? Epsilon into E bar. So now if I write this expression, I can write this in this manner, that is epsilon into what? Epsilon into dou E bar by dou t. So here epsilon is constant, epsilon is not varying with respect to time, right? And hence I can take it outside this differential operation. So if I take it outside, then I can write it as what? Epsilon into dou E bar by dou t, right? Okay, okay. So now if you observe here, Zd is equivalent to what? Zd is equivalent to epsilon into dou E bar by dou t, right? Okay, so if this electric field is not varying with respect to time, if you consider a static electric field here, then it is not going to vary with respect to time. In that case, dou E by dou t will become equivalent to what? Will become equivalent to 0. In that case, Zd will become equivalent to 0. In that case, you don't have any displacement currents. Yes or no here? Okay. And also, if you consider a perfect conducting medium here, if you consider a perfect conducting medium, and we know that inside a perfect conducting medium, the fields are not going to exist. Okay, the fields cannot penetrate inside a perfect conducting medium, right? So which means if you consider a purely conducting medium, right, then this field is not going to then this time varying electric fields cannot penetrate into that medium. So in that case, this term will become equivalent to what? Equivalent to 0. So this displacement currents are associated, only with the dielectric medium. So if you consider a perfect conducting medium, so in that perfect conducting medium, this Zd will be equivalent to what? This Zd will be equivalent to 0, right? Okay, okay. Right. Okay. So whenever you are having a time varying electric field in a dielectric medium, that is going to cause the displacement current density in that medium. right? Okay, so if you are having displacement current density, then you are going to have the displacement current, that is a double integral ZD bar dot dA bar will represent what? Will represent the displacement current. So what is causing the displacement current in a dielectric medium? The time varying electric field in that medium, right? Okay, so this is what you have to understand. So if it is a perfect conducting medium, displacement currents will be equivalent to 0. You are going to have only conduction currents. So if it is a perfect conducting medium, then you are going to have only conduction currents but not displacement currents, right? Okay, okay. So if you consider the medium which is having both conducting nature as well as dielectric nature, then you have to consider both the currents, that is conduction currents as well as displacement currents, right? Okay, okay. So now see here, now I can write finally this modified Ampere's law in this manner, that is the circulation of H field around any closed loop is equivalent to what? Is equivalent to double integral JC bar plus what? ZD bar is nothing but what here? Dou D bar by dou T, dou D bar by dou T dot dA bar, where this JC bar is nothing but what? This JC bar is nothing but sigma into E bar, and this D bar is nothing but epsilon into E bar. Okay, okay. So so for this this is the integral form of what? Integral form of modified Ampere's law. This is the fourth Maxwell's equation, right? Okay, see, it is not compulsory to follow the same order here, first Maxwell's equation, second Maxwell's equation, like that, but anyway we can adopt some convention for our convenience, that's it. Okay, it is not an universal convention to follow, right? Okay. So now if I apply Stokes theorem to this LHS side here, so I am applying Stokes theorem. If I apply Stokes theorem to this LHS side, okay, so we can convert the closed loop line integral into what? Into surface integral with the help of what? Stokes theorem. So that means I can write the above equation in this manner here, that is I can convert this closed loop line integral into surface integral, that is double integral curl of what? Curl of H bar dot what? Dot dA bar is equivalent to what? Is equivalent to double integral JC bar plus dou D bar by dou T dot what? Dot dA bar. Okay, so the surface integration on both sides will get cancelled. So finally what you are going to get? You are going to get curl of H bar is equivalent to what? Curl of H bar is equivalent to JC bar plus what? Plus epsilon into dou E bar by dou T. So I have just replaced this D bar with epsilon into E bar, and I have assumed that epsilon is not varying with respect to time. Okay, then I can write in this manner. So this is the point form or differential form of what? Of modified Ampere's law, right? So this is the integral form, this is the integral form, and this is the differential form, right? Now now if I consider a perfect dielectric medium here, now I am considering a perfect dielectric medium. If I consider a perfect dielectric medium, okay, if I consider a perfect dielectric medium, so perfect dielectric medium means it is a perfect insulating medium, which means the conductivity of this medium is equivalent to what? Is equivalent to 0, right? So in a perfect dielectric medium, if I ask you to write the Maxwell's equations, right, then in this Maxwell's equations, what we have to do? You have to replace wherever you are having sigma, there you have to replace with 0, right? Okay, okay. So if you consider the first Maxwell's equation, so that is the electric flux that is leaving any closed surface is equivalent to the charge enclosed by that closed surface, or you can write the same thing as the electric flux that is leaving any closed surface is equivalent to the charge enclosed by that closed surface divided by epsilon, right? Okay, so this is the integral form. So here if I write a point form, you are going to get divergence of d bar is equal to rho v, and here you are going to get divergence of E bar is equivalent to rho v by epsilon. Okay, so there is no modification in the first Maxwell's equation, because in this equation we don't have any sigma term, right? So the Maxwell's equation will become in the same manner. Okay, there is no modification in the Maxwell's equation. See, just we are imposing this condition here in the Maxwell's equation, and we try to write the Maxwell's equations, right? So in the first equation, since it is independent of sigma, so there won't be any changes in the first Maxwell's equation, right? Okay. Next, if you take the second Maxwell's equation, so what is the second Maxwell's equation here? So that is the magnetic flux that is leaving any closed surface is always equivalent to what? Is always equivalent to 0. This is because of magnetic monopoles doesn't exist, right? Okay. Okay. So what is the differential form or point form here? That is divergence of B bar is equivalent to what? Is equivalent to 0. Okay. So here also this equation also is not going to depend upon sigma. So there will be no change in this Maxwell's equation also, right? Okay. Now if you consider the third Maxwell's equation, what is the third Maxwell's equation here? So that is Faraday's law, right? So what is this Faraday's law? So you have written that the circulation of electric field, around any closed loop is equivalent to what? Is equivalent to minus dou by dou t double integral B bar dot what? B bar dot dA bar, right? So you are going to see the circulation of electric field around a closed loop whenever you are having a change in magnetic flux through that loop. Okay, then only you are going to see the circulation of the electric field. Okay, so a time varying magnetic flux is the cause for what? Is the cause for the circulation of electric field around any closed loop. Okay. Okay, so that's what you have to understand here. So what is causing the circulation of electric field is nothing but a time varying magnetic flux, right? So whenever you are having a time varying magnetic flux, you can see a circulation of electric field around that closed loop. Okay, so if you are having a closed loop like this, and if you are having a time varying magnetic flux through that loop, so because of this time varying magnetic flux, you are going to see the circulation of what? The circulation of electric field around this closed loop. So the cause of the circulation of electric field around this closed loop is nothing but the time varying magnetic flux through this loop. Okay, that's what you have to understand in a brief manner, right? Okay, so now so the cause for this electric field, the circulation of electric field is nothing but time varying magnetic flux through that loop, right? Okay. Okay, next similarly, if you here also in this equation also you don't have any sigma term. Okay, so there will be no change in this Maxwell's equation also in case of perfect dielectric medium, right? Now you can write this in a point form or differential form, that is nothing but curl of E bar is equivalent to what? I can write this as minus dou B bar by dou t, or I can write it as minus mu into dou H bar by dou t, right? In this manner I can represent, right? Okay, now if you observe here, if this magnetic flux is not varying with respect to time here, if this magnetic flux doesn't vary with respect to time, then you are not going to see any circulation of electric field around any closed loop. Okay, so if you are dealing with a static magnetic field, then this B will become constant with respect to time. Okay, so whenever it becomes a constant, let us assume this flux here, this flux, if this flux becomes a constant with respect to time, then in that case what will happen? You are not going to see any circulation of electric field around any closed loop. Okay, you don't have any circulation of electric field around the closed loop if the magnetic flux through this loop is not changing with respect to time. Okay. Okay, so that's what you have to understand here. Next, the fourth Maxwell's equation is nothing but what? Is nothing but the circulation of H field, around any closed loop. So what is causing this circulation of magnetic field around any closed loop here is nothing but the source of this one is nothing but current, right? So this is equivalent to, so you are having two types of currents. So one is conduction current and another one is displacement current. So the conduction current is the current that is associated with the conducting medium. But here we have considered the medium as what here? Perfect dielectric medium. So the conductivity is equivalent to 0, right? So if conductivity is equivalent to 0, the conduction currents in this medium must also be equivalent to what? 0. Yes or no? So in this medium, JC is equivalent to what? Sigma into E, which is equivalent to 0 because sigma is equivalent to 0 here. Right? So you don't have any conduction currents in this perfect dielectric medium. So what are the currents you are going to have? You are going to have only displacement currents, because displacement currents are the currents that are associated with the dielectric medium, and what is going to cause the displacement current is nothing but the time varying electric field in that dielectric medium. Okay, if you are having a time varying electric field in a dielectric medium, then it is going to cause the displacement current. Yes or no? Okay, so because of the displacement current, you are going to have the circulation of magnetic field around that closed loop, right? Now, so here conduction current JC is equal to 0. What you are going to have? You are going to have only double integral ZD bar dot dA bar. So where that ZD bar is nothing but what? Dou D bar by dou T dot what? dA bar. So here also I can write the same equation in this manner. That is, here also here we are doing the differentiation with respect to time and the integration with respect to space. So both the operations are independent to one another. So I can take dou by dou T outside. So I can write this as double integral D bar dot what? D bar dot dA bar. Okay, so this D bar I can replace with epsilon into what? Epsilon into E bar. So I am assuming that this epsilon is independent of this spatial variables. Then I can take it out of this integration, and also I am assuming that this epsilon is constant with respect to time. So here I am assuming that epsilon is independent with respect to this spatial variables, and also it is independent with respect to time. So either with respect to space or with respect to time, it is just behaving as a constant. So you can take it completely out of these operations. So I can write this as what? Epsilon into dou by dou T into what? Double integral E bar dot what? E bar dot dA bar. So this double integral E bar dot dA bar will represent what? Will represent the electric flux. Right? So this electric flux I can represent it as what here? Phi into phi suffix E. So generally we can represent this electric flux with phi suffix E here. Right? So whenever there is a change in electric flux, okay, so it is going to cause what? It is going to cause the circulation of magnetic field around a closed loop. Yes or no? So here we are dealing with what? We are dealing with the perfect dielectric medium. So in a perfect dielectric medium, if you are having a time varying electric flux in that medium, then it is going to cause the circulation of magnetic field in that medium, right? Okay, okay. Now if suppose, now similarly, if you are having, so I can write this B bar as what? This B bar I can write it as mu into what? Mu into H bar. Okay, so if I treat this mu as constant with respect to space as well as time, so then I can write the same expression as minus mu into dou by dou T into what? Double integral H bar dot what? H bar dot dA bar. So in this manner I can represent. Yes or no? Okay, so whenever you are having a change in magnetic flux, it is going to cause the circulation of electric field. Similarly, whenever you are having a change in electric flux, it is going to produce what? The circulation of magnetic field in that medium. So if you consider a perfect dielectric medium, and in that medium, if you are having a time varying if you are having a change in electric flux, it is going to produce the circulation of magnetic field. Okay, it is the cause for the circulation of magnetic field, right? So similarly, in a perfect dielectric medium, if you are having a time varying magnetic flux, if the flux is changing with respect to time. Okay, so then it is going to cause what? Circulation of electric field in that medium. So what is the cause for this circulation of electric field? A time varying magnetic flux. And what is the cause for this circulation of magnetic field? A time varying electric flux. Okay, so if you are having a time varying electric flux, it is causing the circulation of magnetic field. Similarly, if you are having a time varying magnetic flux, it is causing the circulation of electric field in that medium. Right? Okay, so from this what we can conclude here is we are dealing with here, I am considering perfect dielectric medium here, perfect dielectric medium. Okay, now I am taking only this third and fourth equations. I am considering only third and fourth equations. So that is, the third one is the circulation of electric field around any closed loop is equivalent to minus mu into dou by dou t. Okay, so or I can write the same thing as a double integral dou h bar by dou t dot what? Dot dA bar. Right. So similarly, the fourth Maxwell's equation, I can write it as what? Circulation of H field around any closed loop is equivalent to what? So since it is perfect dielectric medium, you are going to have only displacement currents, right? So what you are going to write? What you have to write? So this is nothing but epsilon into double integral dou E bar by dou T dot what? Dot dA bar, right? Okay. Okay. So a time varying magnetic flux is producing the circulation of electric field, and similarly a time varying electric flux is the cause for what? Is the cause for the circulation of magnetic field, right? Okay, so now see here so if suppose if I consider this electric field here, if I consider this electric field, okay, so that is the time varying electric field. So let us say that the time varying electric field I am considering as E of t. Okay, let us assume E of t is equivalent to 2 times of t here. Okay, let us assume the electric field is varying with respect to time as 2 times of t. Let us assume, right? So if I produce an electric field which is varying with respect to time as 2 times of t, that means with respect to time this electric field is increasing. Let us assume, this is just an assumption. Okay, so if you are having this type of electric field, right? So then if you substitute this 2t in this expression, what you are going to get? So the differentiation of 2t is nothing but what? 2, right? So that means this total function you are going to get independent of what? Independent of time. Yes or no here? Because the differentiation of 2t is nothing but what? 2 you are going to get. So which is independent of what? Which is independent of time. So finally whatever the circulation of magnetic field that you are going to get, so that will become independent of what? That will become independent of time. So which means this H field that we are getting here will become what? Will become independent of what? Independent of time, right? Okay, so even though the electric field is varying with respect to time, okay, so this time varying electric field is not producing a time varying magnetic field, right? It is producing a constant magnetic field which is independent of what? Which is independent of time. If suppose this produces a magnetic field which is independent of time here, then what happens? So comes to this equation here, come to this equation. If H field is constant with respect to time, if H field is constant with respect to time, okay, so then what you are going to get? This term will become equivalent to 0, which means this constant magnetic field is not going to produce any circulation of electric field in that medium. Even though the electric field is time varying, it is not producing what? It is not producing, since it is not producing a time varying magnetic field. If it is not producing a time varying magnetic field, then this magnetic flux becomes 0, which means this static field is not going to produce what? Is not going to produce the circulation of electric field in the medium. See, what do you mean by an electromagnetic wave here? What do you mean by electromagnetic wave? So whenever you are having a time varying electric field. So this time varying electric field is going to produce a time varying magnetic field, and this time varying magnetic field in turn is going to produce time varying electric field. So one is going to produce the other, and they are going to travel through space, which we call them as electromagnetic waves. But here according to the definition, I have taken some time varying electric field, but here this time varying electric field is not producing a time varying magnetic field. Since it is not producing a time varying magnetic field, it is not at all producing electric field again. Yes or no? This is not producing electric field again. Understood? So that means here you are going to get the electric field as some constant with respect to time, because this term is becoming 0. So let us assume this is constant with respect to time. If it becomes constant with respect to time, then if you substitute that in this equation, then it is not going to produce again the magnetic field. Understood? So what is the definition of electromagnetic wave? The electric field has to produce the magnetic field, and magnetic field in turn has to produce the electric field. So one has to produce the other, and they have to travel through space. So one is the cause of the other here, right? Okay, if one field ceases to exist, then the other field will also ceases to exist. So it is not going to represent an electromagnetic wave, right? So even though if you are having a time varying electric field, it is not contributing for any electromagnetic wave. Yes or no? So one is not producing the other continuously, right? Okay, so after some time this ceases to exist. Right? Okay, so which means we can conclude that all the time varying fields cannot produce what? Cannot produce the electromagnetic waves. Right? So this is the conclusion we can make. So then which type of fields are going to produce the electromagnetic waves? So if we know that if this term exists, then this is going to exist, and if here this magnetic field becomes function of time, then this term is going to exist. If this term exists, then this term will also going to exist. If here you are getting the electric field as a function of time, then again this term is going to exist. If this term exists, again this exists. If this exists, again this exists. If this exists, again this exists. Okay, so that is the pattern it has to follow in order to produce the electromagnetic wave. So if you observe here, this electric field and magnetic field are related through integrations and differentiations, right? Okay, now which type of time varying function can produce the electromagnetic waves? Which type of time varying function can produce the electromagnetic waves? See, if you consider a sinusoidal function here, so if you integrate that sinusoidal function, if you integrate or differentiate that sinusoidal function, again what you are going to get? You are going to get sinusoidal function only. So if you integrate or differentiate a sinusoidal function some n number of times, still you are going to get what? Sinusoidal function only. So which means we can guess that if this time varying electric field is a sinusoidal function, okay, then this term will always exist. So if this term exists, okay, the final result will be what? If you differentiate a sinusoidal function here, again you are going to get what? Some sinusoidal function here. So which means the circulation of magnetic field, that is H field, you are going to get a time varying function. So if it is a sinusoidal time varying function, then this term is going to exist. If this term exists, then it is going to produce the circulation of electric field. So since H is a sinusoidal function with respect to time, this term will also, you are going to get sinusoidal function with respect to time. Okay, if it is sinusoidal function with respect to time, this electric field will also be what? A sinusoidal function with respect to time. So if it is sinusoidal function with respect to time, then again this term will exist. If this exists, this will exist. If this exists, this exists. If this exists, this will exist. So this process will continue. Yes or no? So that means if you consider a time varying, that means a sinusoidally time varying fields, then it is going to produce what? It is going to produce electromagnetic wave. So one is going to produce the other. So if you consider a sinusoidally time varying electric field in a medium, then it is going to cause the circulation of magnetic field, which is a function of time, and it is also varying with respect to time sinusoidally. and hence this term will not become equal to 0. This is going to produce this one, this is going to produce this one, this is going to produce this one. Yes or no? One is going to produce the other here, right? So that's why all the time varying fields, that's why what is the conclusion we can make here is all the time varying fields cannot produce what? Cannot produce the electromagnetic waves. Then which type of time varying fields can produce the electromagnetic waves? Only the sinusoidally time varying fields can produce the electromagnetic waves. Okay, so if the fields are varying sinusoidally with respect to time, then those fields we call them as what are time harmonic fields. Okay, so throughout our subject here, we are going to deal with what? We are going to deal with time harmonic fields. We are going to deal with time harmonic fields because these are the cause for what? Electromagnetic waves. Yes or no? Okay, what do you mean by time harmonic fields here? So here the fields are varying. The fields are varying sinusoidally. The fields are varying sinusoidally with respect to what? Sinusoidally with respect to time. Then those type of fields we call them as what are time harmonic fields. Okay, so whenever we enter into electromagnetic waves, we are going to consider our electric field and magnetic fields as what are? They must vary sinusoidally with respect to what? With respect to time. So those fields we call them as what? Time harmonic fields. So throughout our subject, we are going to deal with this time harmonic fields. Now, how we can represent this time harmonic fields? See here, this electric field here, this electric field, the electric field in general, it is a function of what? Both space as well as what? Time. Yes or no? It is a function of both space as well as what? As well as time. Right? So with respect to space, I am representing it as E bar of S. This is spatial function. Right? But we know how it has to vary with respect to time. It must be what? Time harmonic fields. So which means it has to vary sinusoidally with respect to time. So that sinusoidal variation with respect to time, I am going to represent as what here? E power j omega t. Okay. So throughout our subject, the fields has to vary with respect to time sinusoidally. So e power j omega t means what here? This represents what? This represents sinusoidally varying fields. Yes or no? Okay. So similarly, if you are having a magnetic field which is a function of what? Space and time. So this is equivalent to what? This is equivalent to h bar of s into what? E power j omega t. So this is how we are going to have E field and H field here. E field and H field. So they must be always time harmonic fields. So in this manner we are going to have the electric field and magnetic field. So they must be time harmonic in nature, right? Okay. Okay. So with the help of Maxwell's equations here, we can get this spatial variation of E bar and the spatial variation of H bar. Right? With the help of Maxwell's equations, we can get the solutions for spatial variations of electric field and magnetic field also. Right? Okay. So finally, once you get this solution, okay. So finally, the total solution is going to represent what? Is going to represent an electromagnetic wave. Okay. So we will see as we proceed into the subject, we will see how we can represent this electromagnetic wave in a through mathematically. Okay, how we can represent mathematically this electromagnetic wave. That means how this solution with respect to space will looks like. If you get this one, then we are going to get the complete solution for the electric field and magnetic field of an electromagnetic wave. So whenever I am talking about electromagnetic wave, you have to understand that that electromagnetic wave is going to have what? Both electric field as well as what? Magnetic field. Right? And that electric field and magnetic field must be what? Must be time harmonic in nature. Understood? Okay? Okay. So is there any doubts up till now? Is there any doubts up till now? Tell me here. Is this clear? Syed Amjad from Madanapalli sir. Okay. Yes, tell me here if you are having any doubts. Is it clear? Ravindra, clear sir. Right. Okay. So keep these points in mind, right? See, you have to keep in mind that this is nothing but what? This is nothing but displacement current. Yes or no? This is nothing but displacement current. See, if suppose the displacement current is not discovered, if we don't know this term, okay, then in that case we know only conduction currents here. We know only conduction currents and we don't know about displacement currents. Okay, then in that case you will write circulation of H field around any closed loop is equivalent to what? Is equivalent to IC only. Right? You don't write displacement current because you don't know about the displacement current. If you don't know about the displacement current, then you don't know about this term. If you don't know this one, okay, then you don't know that a time varying electric flux can produce the circulation of magnetic field around a closed loop. You don't know this one. If you don't know this one, right, then there is no chance for you to predict the existence of electromagnetic waves. Yes or no? If this term is zero, in a perfect dielectric medium, you don't know about displacement current term. Okay, so if you don't know about anything about the displacement current, then this term is not going to exist. Okay, then in a perfect dielectric medium, so we don't know this term also, so it will become simply zero. Right? Then in that case, there is no chance for the prediction of what? Electromagnetic waves. Yes or no? Okay. Okay, so that's why this discovery of displacement current is going to play an important role in the prediction of existence of what? Electromagnetic waves. Okay, so with the help of this displacement current term only, Maxwell has able to predict the existence of what? The existence of electromagnetic waves. He has not discovered the electromagnetic waves, but he has predicted the existence of electromagnetic waves through these Maxwell's equations. Right? Okay. See, if you observe all these four laws here, okay. So all these four laws, whatever I have written here, okay. So all these four laws, we are calling them as what here? We are calling them as Maxwell's equations. But if you remember, we are not calling them as Maxwell's laws. Okay, we are calling them as Maxwell's equations. Why we are not calling them as Maxwell's laws, but why we are calling them as Maxwell's equations means here Gauss has discovered that the electric flux that is leaving any closed surface is equivalent to what? Is equivalent to charge enclosed by that closed surface. So that's why we are calling this as what? Gauss law. So who has discovered this law? Is nothing but Gauss. Right? And similarly, this is we call as a Gauss law for B field. So these laws we are calling them as what? Gauss laws for electric field and for magnetic field. Similarly, this law is discovered by what? Faraday. So that's why we call it as Faraday's law. And this law is discovered, that is circulation of H bar dot dl bar here. So actually the Ampere's law is nothing but the circulation of H field around any closed loop is equivalent to what? Is equivalent to double integral JC bar dot what? dA bar. This is nothing but IC. Okay, so this is what Ampere has discovered. Then Maxwell has modified this Ampere's law by adding a displacement current term to this. Right? Okay. Okay. So this generally we are calling it as what? Ampere's law. Right? Okay. And for every Maxwell's equation, we call them as what? Gauss law for electric field, Gauss law for magnetic field, and then Faraday's law, and then Ampere's law. So whenever I am saying it as law, we are going to mention who has discovered that law, right? Okay, but whenever I am saying as equation, then I am going to mention it as what? Maxwell. Why here? Why means all these laws of electromagnetism, that is Gauss law for electric field, Gauss law for magnetic field, Ampere's law, and Faraday's law, right? So all these laws of electromagnetism was formulated into 4 simple mathematical equations by whom here? Maxwell. So Maxwell has formulated all these 4 laws of electromagnetism into 4 simple mathematical equations. So the mathematical forms of these laws is given by whom? Is given by Maxwell. So that's why whenever you are representing in this mathematical form, we call them as what here? We call them as Maxwell's equations. We call them as Maxwell's equations. Okay? Okay. We don't call them as Maxwell's laws. We call them as Maxwell's equations, because Maxwell has formulated all these laws of electromagnetism into these mathematical equations. So that's why these equations are called as Maxwell's equations, right? Okay. 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 So this is all about Maxwell's equations here, right? Okay. So next we will see wave propagation. Next topic we will see wave propagation in different media. Wave propagation in different media. Okay, wave propagation, that means we are going to study about the wave propagation characteristics in a different media, right? Okay. Okay. Right. Okay. So first I am going to make some assumptions regarding the media. So we are assuming that the electromagnetic wave is propagating in a medium, right? So if the medium characteristics changes, then the propagation characteristics of that particular electromagnetic wave is also going to change, right? So how those propagation characteristics are going to change if you change the medium, right? That's what we are going to study here, right? Okay. Okay. So first of all, we are going to make some assumptions regarding the medium. So what are those assumptions here? So we are making some assumptions regarding the medium. Assumptions regarding the medium. Regarding the medium in which our electromagnetic wave is going to propagate. Okay. So we are making some assumptions regarding the medium in which our electromagnetic wave is going to propagate, right? Okay. So the first assumption we are making here is we are assuming that the medium as infinite here. The medium as infinite or unbounded. Okay. So we are assuming our medium as what? Our medium as infinite or unbounded. This is the first assumption we are making. I hope you know what do you mean by infinite or unbounded. Okay. So whatever the medium that we are considering, we are assuming that that medium has extended up to what? Has extended up to infinity. So there are no boundaries to that medium. Okay. So that's why we call it as infinite or unbounded medium, right? Okay. Next, the second assumption we are making is we are assuming the medium as linear. We are assuming the medium as linear. I will tell what do you mean by linear, right? Okay. Okay. So similarly, we are going to assume the medium as a isotropic. I will explain here what do you mean by this linear, what do you mean by this isotropic and all these things. Okay, linear, isotropic and homogeneous. Homogeneous and then source free and then lossless. Okay, so these are the assumptions we are making here. So what are the assumptions we are making regarding the medium? We are assuming the medium as infinite or unbounded, and also we are assuming that medium as what? We are assuming the medium as linear, isotropic, homogeneous, source free and lossless. Right? Okay. So what do you mean by linear? What do you mean by linear? See, so these are the assumptions regarding what? Regarding the medium. See, what are the properties of a medium here? How we can define the properties of a medium? Tell me. How we can define the properties of a medium? See here, if you consider epsilon here, epsilon. So we call this as what here? We call this as a permittivity of the medium, right? We call this as a permittivity of what? Of medium. Permittivity of medium, right? If you say mu, what we are going to say? Mu is nothing but permeability of what? Permeability of medium. Permeability of a medium. And if I say sigma, what do we say? Sigma is nothing but conductivity of a medium. Conductivity of medium, right? Okay, so epsilon is called as permittivity of the medium, mu is called as permeability of the medium, sigma is called as conductivity of the medium. So all these three parameters are nothing but what? Are going to decide the properties of what? The properties of a medium. Yes or no? Yeah. Okay, so this will tell you about the permittivity of the medium, and this will tell you about the permeability of the medium. This will tell you about the conductivity of the medium. So these three parameters we can call them as what here? These are nothing but the properties of the medium. So we can define the properties of the medium in terms of epsilon, mu and sigma, right? Okay, so now here we are making the assumptions regarding the medium. That means we are making the assumptions regarding this epsilon, mu and sigma of that particular medium, right? Okay, okay. So here, what do you mean by linear medium here? So here the linear medium means whenever the electromagnetic wave is propagating, whenever the electromagnetic wave is propagating in a medium, you are going to have what? You are going to have oscillating electric field. Oscillating means it is oscillating sinusoidally here, right? So that is, it is time harmonic fields. You have to keep that point always in mind, right? Okay, so you are going to have oscillating electric field, that is time varying electric field, and also you are going to have a time varying magnetic field, right? So whenever the electromagnetic wave is propagating in a medium, so this electromagnetic wave is going to have oscillating electric field as well as what? Oscillating magnetic field, right? So this oscillating electric field and oscillating magnetic field are not going to disturb the properties of the medium. Then we call that medium as what here? Linear. Okay, so whenever the electromagnetic wave is propagating, you are going to have oscillating electric field and oscillating magnetic field. So we are assuming that epsilon, mu and sigma of that particular medium is not going to get disturbed by this oscillating electric and magnetic fields. Okay, then that medium is said to be what? Is said to be linear. Okay, so whenever the wave is propagating, this oscillating electric and magnetic fields are not going to disturb the properties of the medium. Then in that case, we call that medium as what here? Linear. Okay, so here I can simply write in this manner, that is epsilon, mu and sigma are not going to get disturbed, by what? By the oscillating E and H fields here. See, if you don't understand these things here, if you don't understand these things, then you will definitely do the mistakes in the questions. Okay, okay, you must be clear with these concepts here, right? See, whatever the problems they are giving in EMT, okay, so mathematically they are going to be very, very simple, but you have to understand the concepts in a crystal clear manner, then only you can answer those questions. So mathematically they won't be tough at all, they are going to be very simple in terms of mathematics, right? But conceptually, if you understand, then only you can answer the questions in EMT. Okay, okay. Oh, Praveen, what you are asking here? MSc फिजिक्स का स्टूडेंट हूँ तो गेट एग्ज़ाम के लिए गेट अकेडमी ज्वाइन कर सकता हूँ. Okay, I don't know whether MSc physics is available or not, right? Okay, you can contact the management here, right? Okay, next here. Next, what do you mean by isotropic medium? What do you mean by isotropic medium? So isotropic medium means we are assuming that the medium properties epsilon, mu and sigma are independent of what? Are independent of, are uniform, or uniform, not uniform. Homogeneous means epsilon, mu and sigma. Okay, epsilon, mu and sigma are direction independent here, or direction independent. Are direction independent. So that means we are assuming them as what here? We are assuming them as scalars, right? Okay. So what do you mean by isotropic here? Isotropic medium means we are assuming that the medium properties epsilon, mu and sigma are what? Are direction independent. So if they are direction independent means we are treating this epsilon, mu and sigma as what? As scalar quantities. Okay, then we call that medium as what here? Isotropic, right? Next, what do you mean by homogeneous? What do you mean by homogeneous? So homogeneous means here we are assuming that epsilon, mu and sigma are uniform, throughout the medium, are uniform throughout the medium, are uniform throughout the medium. Are uniform throughout the medium means what here? If suppose if you are at this location in space, so at this location whatever the values of epsilon, mu and sigma you are going to see, so throughout this medium, throughout the medium, at each and every location you are going to see the same values of epsilon, mu and sigma, then we call that medium as what here? Uniform. So throughout the medium, these properties of the medium are going to be uniform. So at each and every location these values are not going to change, they will be uniform throughout the medium. Okay, so which means I can simply say that this epsilon, mu and sigma are independent of what? Are independent of space. At each and every location in space, if they are uniform, then we call that medium as what here? Homogeneous, right? Okay, so in brackets you can write here epsilon, mu and sigma are independent of what? Are independent of what? Independent of space. So that's what we are assuming here, right? Then we call the medium as what here? Homogeneous, right? Okay. Next, what do you mean by source free here? What do you mean by source free? So source free means we are going to assume the charge densities within the medium are equivalent to 0. So that means source is nothing but what? Charge. Yes or no? Okay, so that is rho v we are going to consider as what? Rho v we are going to consider as 0. The charge densities in the medium we are going to assume it as what here? 0, right? And what do you mean by lossless? What do you mean by lossless? So lossless means the condition here is we are assuming here epsilon r and mu r, that is relative permeability and relative permittivity and relative permeability, we are assuming them as real quantities. We are assuming them as real quantities, and also we are assuming that sigma is equal to what? Sigma is equal to 0. So if it satisfies these two conditions, okay, so that is epsilon r and mu r must be what? Must be real quantities, and the conductivity of the medium is equivalent to 0. Then it is going to behave as what here? It is going to behave as a lossless medium. Then that medium is going to behave as lossless medium, right? Okay, so this is the condition for lossless medium, right? So these are the assumptions we are making regarding the medium here. So what are the assumptions? We are assuming our medium as infinite or unbounded, and also we are assuming our medium as linear, and also we are assuming our medium as isotropic, homogeneous, source free and lossless, right? So what do you mean by linear? Linear means the medium properties are not going to get disturbed, okay, are not going to get disturbed by the oscillating electric and magnetic fields, right? Then we call that medium as linear. What do you mean by isotropic? So here, if epsilon, mu and sigma are independent of direction, that means if they are direction independent, okay, then we call that medium as what here? Isotropic, right? So that means we are treating epsilon, mu and sigma as scalar quantities, right? Next, what do you mean by homogeneous? Homogeneous means the medium properties are uniform throughout the medium, which means this medium properties epsilon, mu and sigma are independent of what? Are independent of space, right? So source free means rho v is equal to 0, and lossless means epsilon r and mu r must be real quantities, and also sigma must be equivalent to what? Sigma must be equivalent to 0. If it satisfies these two conditions, then only it is going to behave as what? Lossless medium. Then only it is going to behave as lossless medium. Okay. So in general, epsilon r and mu r can also be what? Can also be complex quantities. So whenever they are complex quantities, then it is not going to behave as lossless medium. Even though conductivity is equal to 0, if epsilon r and mu r becomes complex quantities, then in that case it is not going to behave as lossless medium, right? Okay, this point is very, very important. So when a medium is going to behave as lossless medium, if epsilon r and mu r both must be real, at the same time conductivity of that medium must also be equal to 0. If it satisfies these two conditions, then only the medium is going to behave as what? Lossless medium, right? Okay. Right. Kalyan Chakravarti, sir, what about non-dispersive medium? We will talk about dispersive and non-dispersive mediums also here. Okay, as we proceed into the subject, we will talk about those things also. Don't worry. Right? Okay. Epsilon r and mu r are real quantities. Okay, so these are the assumptions we are going to make regarding the medium, right? Okay, so I will give you one question here. In a non-homogeneous medium, medium, okay, non-homogeneous, or sometimes they can call it as inhomogeneous. Both mean same here. Okay, in a non-homogeneous or inhomogeneous medium, which of the following following Maxwell's equations are correct? Which of the following Maxwell's equations are correct? Okay, what I have given in a non-homogeneous medium, which of the following Maxwell's equations are correct, right? So the first one, option A, I am giving divergence of E bar is equivalent to rho v by epsilon. Option B, I have given divergence of D bar is equivalent to rho v. And option C, divergence of B bar is equivalent to 0. Option D, divergence of H bar is equivalent to 0. Okay, so in a non-homogeneous medium, which of the following Maxwell's equations are correct? See, if you don't know the what do you mean by homogeneous and what do you mean by non-homogeneous, okay, then you cannot answer this question, right? Okay, so purely conceptual here, almost all the questions, 99% of the questions in EMT are purely conceptual, right? Okay, okay, so tell me the answer here for this question. Tell me the answer for this question. In a non-homogeneous medium, which of the following Maxwell's equations are correct? Which of the following Maxwell's equations are correct? Tell me. In a non-homogeneous medium, which of the following Maxwell's equations are correct? Okay. Tell me here. So see here. See, they have given the medium as what here? They have given the medium as inhomogeneous or non-homogeneous. Okay. So what do you mean by homogeneous medium here? Homogeneous medium means what? Means epsilon, mu and sigma are uniform throughout the medium. That means epsilon, mu and sigma are independent of what? Are independent of space. Then we call that medium as what here? Homogeneous medium. So inhomogeneous or non-homogeneous means what here? Epsilon, mu and sigma will become functions of what? Will become functions of space, right? So they are non-uniformly distributed throughout the space. That's what you have to understand by non-homogeneous medium or inhomogeneous medium. Okay, so this means epsilon, mu and sigma are functions of what? Are functions of space. Are functions of space. Then we call that medium as inhomogeneous. So if they are functions of space here, then see here, if I write the Maxwell's equation, I am writing the Maxwell's equation, that is point form or differential form in this manner, that is divergence of D bar is equivalent to what? Is equivalent to rho v, right? Okay, now this D bar is nothing but what? This D bar is nothing but epsilon into what? Epsilon into E bar. So this divergence operation is nothing but what? Is nothing but spatial operation. Yes or no here? This is nothing but spatial operation, right? Okay, okay. So here epsilon into E bar. Now if the medium is if the medium properties epsilon, mu and sigma are functions of space here, are functions of space, okay, then in that case you cannot treat this epsilon as independent of space. Yes or no? Because in inhomogeneous medium this epsilon becomes a what? Function of space. So here epsilon is a function of space and the electric field is also a function of space. Here epsilon is not acting like a constant with respect to what? With respect to spatial operation, right? It is also varying with respect to space. So if you know that variation, then only we can perform this divergence. Now here we cannot treat epsilon as what? Constant with respect to this spatial operation, right? And hence you have to write this Maxwell's equation in this manner only, that is divergence of d bar is equivalent to rho v. You cannot take epsilon outside this operation. Why? Means now epsilon is not constant with respect to space, right? So if suppose in case of homogeneous medium here, if I consider homogeneous medium, then in that case I can write the expression in this manner, that is divergence of d bar is nothing but epsilon into E bar, which is equivalent to rho v. Now here in homogeneous medium, so epsilon, mu and sigma are independent of what? Space, right? So here this epsilon is independent of what? Independent of space. So that means with respect to space it is going to act like a constant. So you can treat it as constant with respect to this spatial operation, right? So you can take this epsilon outside this operation. So then you can write it as what? Epsilon into divergence of E bar is equivalent to rho v. So then you can write divergence of E bar is equivalent to what? Is equivalent to rho v by epsilon. Right? Okay. So only in case of homogeneous medium you are having this freedom. You can take epsilon outside this operation and you can write the Maxwell's equation in this manner, right? Whereas in case of inhomogeneous or non-homogeneous medium, you cannot treat this epsilon as constant with respect to this operation, and hence you cannot take this epsilon out of this operation. Understood? Okay, so if they are saying the medium as non-homogeneous or inhomogeneous, then which one of these Maxwell's equations are correct here? In an inhomogeneous medium, you have to write always the Maxwell's equation as a divergence of d bar is equivalent to rho v. You should not write it as what? You should not write it as divergence of E bar is equal to rho v by epsilon. So we'll get this equation if and only if we treat epsilon as constant with respect to what? With respect to this spatial operation. Understood? Okay, and hence in case of inhomogeneous medium, we cannot write the Maxwell's equation in this manner, right? So that means this option A is what? Option A is wrong, whereas option B is what? Option B is correct. We have to write the Maxwell's equation in this manner in case of inhomogeneous medium, right? Okay, yeah. Next, similarly, if you take another Maxwell's equation, that is divergence of B bar is equivalent to 0. Here also the same logic here. So here B bar is nothing but what? B bar is nothing but mu into what? Mu into H bar. So in a inhomogeneous or non-homogeneous medium, this mu becomes a function of space, and hence you cannot treat it as a constant with respect to space. So in that case you have to always write it as what? Divergence of B bar is equal to 0 only. So if it is homogeneous medium, okay, then what will happen? Mu becomes constant with respect to space. Then you can treat it as constant with respect to this spatial operation and you can take it out of this operation. Okay, so then in that case I can write the same equation as mu into divergence of H bar is equal to 0. In that case I can write divergence of H bar is equal to 0. Okay, because I am taking this mu to this side, then I can write this equation as divergence of H bar is equal to 0. So this is possible, this equation is possible only in case of what? Homogeneous medium, right? Okay, because here in inhomogeneous or non-homogeneous medium, since mu is a function of space, you cannot treat it as a constant. So always you have to write divergence of B bar is equal to 0 in case of what? In case of inhomogeneous medium. You cannot write as divergence of H bar is equal to 0, right? Okay, and hence which option is correct here? Divergence of B bar is equivalent to 0. So this option is also correct. So option B and option C are correct, whereas this option A and option D are wrong. So you can answer this type of questions if and only if you know what do you mean by homogeneous medium, right? So they will give some conditions regarding the medium. So you have to apply those conditions to the medium, and you must be able to write, okay, you must be able to write the Maxwell's equations by imposing those conditions, right? Okay. So that's what you have to understand. So here in this case, option B and option C are correct, whereas option A and option D are wrong, right? Okay. So I hope this point is crystal clear here. I hope this point is crystal clear, right? Okay. Okay. So here I am taking a break here. We'll take break. Okay. Break for 5 minutes. We'll take break for 5 minutes, right? Okay. So now the time is 11:55. Now the time is 11:55. So we'll meet at 12 o'clock here. Okay. We'll meet at 12 o'clock. Right. So take break for 5 minutes. Again we'll meet at 12 o'clock. Right. Okay. So take break here. Take break. Hello. Okay. Okay, yaar. So welcome back. So first of all, let me know, is audio and video everything is clear? So if it is clear, we will continue here. So let me know whether audio and video everything is clear. Anybody please confirm that in chat box so that we can continue. Is audio and video everything clear? Is audio and video everything is clear? Tell me here. Okay. Okay. Right. Right. So here so we have made these assumptions regarding the medium. So until I specify, we are going to assume the medium as what? Infinite medium, and we are going to assume the medium as linear, and we are going to assume the medium as isotropic, and we are going to assume the medium as homogeneous, and we are going to assume the medium as what? The medium as source free. Okay, and we'll try to study for a lossless medium, and also we try to study how the fields are going to be in a lossy medium. Okay, so all these other assumptions will be same here. So throughout our lecture, all these assumptions will be same, whether it is lossy medium or lossless medium. Okay, so we are assuming the medium as infinite, linear, isotropic, homogeneous, and source free. Right. So first we will deal with lossless medium, then we will go for lossless medium. So we are analyzing the propagation characteristics of our electromagnetic wave in case of lossless medium, and then we are going to analyze in case of what? Lossy medium. So remaining all the properties will be same here, will be same. Right. Okay. Okay. So first we'll start with a lossless medium. So first we'll start with a lossless medium. Lossless medium. So lossless medium means the condition is nothing but what? Epsilon r and mu r must be real quantities, and conductivity of the medium must be equivalent to what? Must be equivalent to 0. So if it satisfies both the conditions, then we can call that medium as what? We can call that medium as lossless medium. Right? Okay. See, I have already told that the electric field and magnetic field are nothing but what? Are nothing but functions of space and time, right? And they must vary sinusoidally with respect to time. So the solutions of electric field must be like this, right? And the solution of magnetic field must be like this, h bar of s into e power j omega t. So they must be time harmonic in nature. So this is what we have already seen, right? Okay. Okay. So now see here. So here the spatial function means what? Spatial function means it may be a function of what? X, y, and z. It may be a function of x, y, and what? And z. Right? Okay. Okay. So if the fields are functions of all the three variables x, y, and z, then it is going to represent a three-dimensional wave. Okay, if electric field varies with respect to x as well as y as well as z, similarly if the magnetic field varies with respect to x, with respect to y, with respect to z, then in that case we call these solutions of electric field and magnetic field as what here? As a three-dimensional wave. Suppose if it is a function of only two variables, if these fields are functions of two spatial variables, then we call that wave as what here? Two-dimensional wave. And similarly, if these fields are functions of, especially if they are functions of only one variable, then we call them as what here, one dimensional wave. So first we will start our analysis with respect to one dimensional wave. Okay, now let us assume the wave is propagating in z direction. I am assuming that the wave is propagating in z direction. If I assume that, then this electric field and magnetic field will become functions of what? Functions of only z. Yes or no? Okay. Okay. So here I am assuming wave is propagating. Wave is propagating in z direction. So in that case, the electric field will become a function of what? Spatially, it will become a function of only z. Okay. Always it must be a function of time, and it has to vary with respect to time sinusoidally. That you have to keep in mind. Okay. Okay. So E bar of z comma t is equivalent to, I can write it as what? E bar of z into what? Into e power j omega t. So similarly, I can write h bar of z comma t is equivalent to what? Is equivalent to h bar of what? H bar of z into what? Into e power j omega t. So if you remember here, this e bar of z, it is a vector function which is a function of z. Since it is a vector quantity, it can have what? It can have x component, y component as well as z component. Yes or no? See, this e bar of z is nothing but what? It can be written as ex of z ax cap plus what? Ey of z ay cap plus what? Ez of z az cap. In this manner we can represent. Right? Okay? Okay. So keep this point in mind. So this is a vector function which is a function of only z. So this represents a one-dimensional wave. This represents one-dimensional wave. Right? Okay? Okay. So this represents a one-dimensional wave. One-dimensional wave. Right? Okay. Okay. Right. So here with the help of Maxwell's equations, we can get the solutions for this E bar of z and H bar of z also. But here I am not going to deal with the derivations here. Right. So I will give you how they are going to vary spatially, how the solutions we are going to get with respect to space. Okay, that's what I am going to tell. Right. Okay. So here for E bar of z here, for E bar of z, right. So the solution will be like E into e power minus gamma z plus E into e power gamma z. Okay, this is the solution you are going to get. Right. Now here if you substitute this is the solution with respect to what? With respect to space you are going to get. So you are going to get this solution with the help of the Maxwell's equations. So just by taking third and fourth Maxwell's equations, okay. So if you do some mathematical simplification, you are going to get the wave equation. So from that wave equation, you are going to get the second order differential equation. So for that second order differential equation, if you determine the solution, then you are going to get the solution in this manner. So this is the solution with respect to space. Okay. So similarly you can get the solution for H field in the same manner, whereas in place of E you have to keep H. That's the only difference. Okay. If you analyze with respect to electric field, the same type of analysis is equivalently valid for magnetic field also. Okay. So there is no need to study electric field separately and magnetic field separately. So if you are studying about electric field means simultaneously you are studying about magnetic field also. Understood? Because both are related to what? One another. So one cannot exist without the other. So whatever the analysis we are doing with respect to electric field, the same analysis is equivalently valid with respect to magnetic field. So here you cannot see the electric field separately and magnetic field separately. Both will become a single phenomena. Without E field there is no H field. Without H field there is no E field. Understood? Okay. Okay. So now see here. So this is what you are going to get. Now what is the complete solution you are going to get? E bar of z comma t is equivalent to what? Is equivalent to e into e power minus gamma z. I will tell what is this gamma and all. Okay. So e into e power minus gamma z into what? Plus e into e power gamma z. So multiplied by this, multiplied by e power j omega t. Right. Okay. So this is nothing but what? This is nothing but e bar of z. Right. So this is the solution you are going to get. Now here this gamma here. So what is this gamma? So this gamma is called as a propagation constant. This gamma we call it as what? Propagation constant. Okay. So in general this gamma is a complex quantity. In general this gamma is a complex quantity. So it is going to have both real part as well as what? Imaginary part. So the real part of gamma is represented with alpha, which we call it as a attenuation constant. This is called as attenuation constant, right? And the imaginary part of gamma we call it as what? Beta. So this is called as a phase constant. This is called as phase constant. And the units of this gamma, is nothing but meter inverse, right? Whereas the units of alpha is nothing but Nepper per meter, whereas the units of beta is nothing but what? Is nothing but radian per meter, or you can express in terms of what? Degree per meter also. Okay. So the units of alpha is Nepper per meter and the units of beta is radian per meter, and we can express the units of alpha in terms of what? dB per meter also. So the relation between the Nepper and dB are, the relation between Nepper and dB is 1 Nepper is equivalent to 8.68 dB. So this is very important relation. So it can be used to convert from Neppers to what? Neppers to dB, or 1 dB is equivalent to what? 1 by 8.68 Neppers. Okay. So we can express alpha either in terms of Nepper per meter, or we can express it in terms of dB per meter, but in general by default we are going to represent in terms of Nepper per meter. Okay. If they specifically ask to express in terms of dB per meter, then by using this conversion relation you can easily express alpha in terms of what? dB per meter also, right? Okay. Okay. So so 1 Nepper is equivalent to 8.68 dB, right? So here this gamma, so what it is going to tell you is how the propagation characteristics of the wave. This is called as what? Propagation characteristic. Yes or no? This is called as propagation constant. Propagation constant. So what this propagation constant tells you is it tells you about how the propagation characteristics of the wave are going to change for every meter as the wave propagates in a medium. How the propagation characteristics of a wave are going to change for every meter as the wave propagates in a medium. So per meter how this alpha is going to change and how this beta is going to change. So that's why the units are nothing but per meter. So that is meter inverse. Okay. So that is nothing but gamma r. Okay. I am not writing all the definitions and all. Okay. You have to write your own notes here because the time is limited. So within this time limit I am trying to cover most of the topics here, right? Okay. So next alpha. What do you mean by alpha? Alpha is called as attenuation constant. So it tells you how the amplitude of the wave, is decaying for every meter as the wave propagates in a medium. So that is called as attenuation constant. And what is this beta? Beta represents a phase constant. It tells you how the phase of the wave, is changing for every meter as the wave propagates in a medium. So that's what given by phase constant here, right? Okay. See, for any wave, what are the main characteristics of the wave here? So its amplitude and phase. So how the amplitude of the wave is decreasing or decaying exponentially, how the amplitude of the wave is decaying, okay, per meter as the wave propagates in a medium, that is decided by alpha, and how the phase of the wave is changing for every meter as the wave propagates in a medium, that is decided by beta. Okay, so if you combine this both, this is regarding to amplitude and this is regarding to phase, right? So if you combine these two, you are going to get what? The overall propagation constant of the wave, right? Okay, so gamma is called as propagation constant and alpha is called as attenuation constant and beta is called as a phase constant. So all are defined per meter here. For every meter, how the amplitude of the wave is decaying, and for every meter, how the phase constant of the wave is changing, right? So that is decided by this propagation constant, right? Okay, okay. So now, if I substitute this alpha plus z beta in place of gamma, what you are going to get? So in place of gamma, I am substituting alpha plus z beta. So here I am substituting alpha plus what? Alpha plus z beta, right? So if you substitute that, then I can write the complete solution in this manner. So that is E bar of z comma t is equivalent to what? Is equivalent to E into, so e power minus gamma z. So in place of gamma, I am replacing with alpha plus z beta. So then I can write it as what here? E power minus alpha z multiplied by what? E power j omega t multiplied by what? E power minus j beta z. Okay, you are going to get here e power minus alpha z multiplied by e power minus j beta z multiplied by e power j omega t. Okay, so here you are going to get e power minus alpha z into e power minus j beta z into e power j omega t plus here you are going to get e into what? E into e power alpha z. Here you are going to get e power j beta z multiplied by what? E power j omega t, right? Okay, so I can write this as e into e power minus alpha z. So this represents what? This represents the amplitude of the wave. This represents the amplitude of the wave. Next, I can write this one as what here? E power j of what? J of omega t minus beta into z. And similarly, the second term, I can write it as what? I can write it as e into e power alpha z into e power j of what? Omega t plus what? Plus beta z, right? Okay, okay. So here this is the amplitude. Here this is the amplitude. This is amplitude, and this represents what? This represents a phase of the wave. This represents a phase of the wave, right? Okay, okay. Now see here, this is the amplitude of the wave and this is the phase of the wave. So based on this phase of the wave, we can tell whether the wave is propagating, in positive z direction or negative z direction. So remember this one, how we can tell is if the polarity before omega t, and the polarity before beta z, if the polarity before omega t and the polarity before beta z, that is if the sign before omega t and the sign before beta z, if both are of opposite polarity, then remember that the wave is propagating in positive direction. Okay, if you observe here, before omega t you are having plus and before beta z you are having minus. So since both are of opposite polarity, here this represents a wave propagating. This represents a wave propagating in which direction here? In a positive z direction. Wave propagating in positive z direction, right? Okay, and here it represents what? See, if the polarity before omega t and the polarity before beta z, if both are of same polarity, it may be both are of plus sign or it may be both are of minus sign. Okay, if they are having same polarity, then in that case remember that the wave is propagating in negative direction. The wave is propagating in negative direction. So here this represents a wave that is propagating in negative z direction. in negative z direction. Wave is propagating in negative z direction, right? Okay, so that means the solution of this electric field of an electromagnetic wave, what we got? We got it as a forward traveling wave, that is the wave propagating in positive z direction. Generally we call it as forward traveling wave, and here we got the wave that is propagating in negative z direction. Okay, so this is, we can call it as a backward wave, right? Okay, so we are getting both a forward wave as well as what? Backward wave. So the superposition of these two here, the superposition of forward traveling wave and backward traveling wave is going to form what? It is going to form standing wave pattern. So if you are having both forward traveling wave as well as what? Reflected wave or backward traveling wave. So the superposition of this forward traveling wave and backward traveling wave is going to form what? Is going to form standing wave pattern. It is going to form the standing wave pattern. Okay, but when this standing wave pattern is going to be possible? Whenever you are having both forward wave as well as what? Backward wave. Whenever both the waves are present in the medium, then only this standing wave pattern solution is possible. But here we are making some assumption regarding the medium, that is we are assuming our medium as what here? We are assuming our medium as a homogeneous. So homogeneous means what? Epsilon, mu and sigma are what? Are uniform throughout the space. Right? So that means the medium properties are not at all changing throughout the medium. So if the medium properties are not at all changing throughout the medium here, then in that medium, can you see any backward traveling wave or can you see any reflected wave? See, that means if you are having a wave that is propagating in positive z direction, let us assume this is positive z. If the wave is propagating in positive z direction, right? So at each and every location in this medium, if the medium properties are uniform, that means at each and every location the values of epsilon, mu and sigma are same. The medium properties are not at all changing. Okay, if the medium properties are not at all changing, then if the wave is propagating in positive z direction, then it continues to propagate in positive z direction only. Because everywhere the medium properties are uniform, they are not changing, and hence you are not going to see any backward traveling wave. So when you are going to see a backward traveling wave here, whenever the wave is propagating from one medium to another medium. So one medium to another medium means what here? In this medium the medium properties are different, and in another medium the medium properties are different. So if the wave tries to propagate from one medium to another medium, then what you are going to see? So a part of the wave is going to get transmitted into the other medium, and a part of the wave will get reflected back into the same medium. Okay, and hence in this medium you are going to have both forward wave as well as what? Backward wave. So both forward wave as well as backward wave is possible if and only if the medium is non-homogeneous. Yes or no? If the wave tries to propagate from one medium to another medium. Okay, so here the medium properties are different, and in another medium the medium properties are different. That means the overall the medium is non-homogeneous. Right. So in this case what will happen? As the wave propagates from one medium to another medium, because of changes in the medium properties, what will happen? A part of the wave will get transmitted into the other medium, and a part of the wave will get reflected back into the same medium. So which means you are going to see both forward wave as well as backward wave. Okay, if you consider the total medium, as homogeneous medium. So if you consider the total medium as non-homogeneous medium. If you consider the total medium as homogeneous, then there will be no change in the medium properties. In that case, you are going to see only the forward traveling wave. Or if the wave is propagating in negative z direction, let us assume, then it continues to propagate in negative z direction in case of what? In case of homogeneous medium. So that means in homogeneous medium, either forward traveling wave is possible or backward traveling wave is possible. Both the waves simultaneously is not at all possible if you are considering the total infinite media as homogeneous. So since here we are treating our medium as homogeneous, the total infinite media we are treating it as homogeneous. So in that case, either forward traveling wave is possible or backward traveling wave is possible. So both the waves simultaneously is not at all possible. That means this standing wave pattern is not at all possible. Okay, here if I assume the wave is propagating in positive z direction, then it continues to propagate along positive z only. So in this case, you are not going to see any backward wave. Okay, so the solution for the electric field or magnetic field in a homogeneous medium must have what? Must have only traveling wave pattern. So it must be either forward traveling wave or it can be backward traveling wave. But both cannot exist in case of what? In case of a homogeneous medium. So that's what you have to understand, right? Okay. Okay. So here if I assume the wave is propagating in positive z direction, so then I can write E bar of z comma t is equivalent to what? Is equivalent to some e into e power minus alpha z. So I am considering only function here, right? So e into e power minus alpha z into what? Into e power j of omega t minus beta z. Okay, so in this manner you can write the solution. Or if you consider only backward traveling wave, then you have to write e into e power alpha z into e power j of what? Into e power j of omega t plus beta z. Then in that case you should not consider this one. You have to consider only this one, right? And remember here the z value is going to be what? Z value is going to be negative, right? Okay. Okay. Right. So if I consider the forward traveling wave, so then this is going to be the solution. This is going to be the solution. So this is the amplitude. This is the amplitude, right? Okay. So what alpha says here? Alpha says how the amplitude is going to decay for every meter, right? Then what is this alpha z says here? Alpha z says the overall attenuation over what? Over z meters. Alpha says the attenuation per meter. If the wave travels over z meters, then the overall attenuation will be what? Alpha z. So alpha z represents what? Represents overall attenuation. Overall attenuation. Overall attenuation over z meters. Over z meters. Right? Okay. So similarly here beta represents what here? Beta represents the change in phase per meter. Yes or no? Change in phase per meter. So if the wave propagates over z meters, then what is the overall change in phase with respect to space here? See, if you observe here, this beta z is the phase with respect to what? With respect to space. With respect to space, right? And here omega t represents what? Represents the phase with respect to what? With respect to time. Yes or no? So whenever you are representing the phase, the overall phase is going to have the phase with respect to time as well as it is going to have phase with respect to space, right? So the space with respect to space we are going to represent here as beta z in case of one-dimensional wave, and if the wave is propagating in z direction, right? And this omega t represents the phase with respect to what? With respect to time, right? Okay. So whenever we want to analyze the spatial variations, we can freeze the time here. We can make some time constant. Okay. So at that particular instant of time, we can observe the spatial variations of the wave, right? Or if you want to observe the time variations of the wave, then in that case you have to fix the location. That means you have to keep z as constant. If you fix the location, that is if the z value is constant, then this beta z is going to be constant. Okay, so in that case, if you vary only time, then you can observe at that particular location, you can observe what? You can observe the time variations of the electric field. Okay, so if you want to observe the spatial variations of the field, then you have to freeze the time. And similarly, if you want to analyze the time variations of the field, then you have to fix the space, right? In this manner, we can analyze both the time variations as well as what? Spatial variations, right? Okay. Okay. So what I am saying here, alpha z represents the overall attenuation over z meters, isn't it? Okay. gate with fun. What is the use of standing wave? I will tell you. You will encounter this standing wave patterns in case of what? In case of transmission lines. Okay, there we are going to analyze with standing waves. So I will explain what is the nature of standing wave, what is the difference between traveling wave and standing wave. All those things I will explain. Right? Okay. So beta represents what? Beta represents a change in phase per meter. Okay. So beta z represents what here? Beta z represents what is the overall change in phase over what? Over z meters. Okay, it represents the change in phase. You can write simply change in phase over what? Over z meters. Over z meters. Okay, so if the wave propagates over z meters, if you want the overall attenuation, that overall attenuation is given by alpha z. So what is the units of this overall attenuation here? So alpha units are nothing but Nepper per meter. For z the units are meter. So meter will get cancelled. So the units are nothing but what? Nepper, or we can express it in terms of what? dB also. Right. So similarly beta z, for beta z, what are the units here? For the units of beta is nothing but radian per meter, and the units of z is meter. So meter will get cancelled. So the units of beta z is nothing but what? Radian, or you can express in terms of degree also. Okay. Okay. So generally we are going to represent the solution for the electric field. The solution for the electric field in this manner. In this manner. Right. So that is you are going to have amplitude and you are going to have phase of the wave. And if you observe here, alpha here is not equivalent to 0. Okay, here alpha is not equivalent to 0. If alpha is not equivalent to 0, then what will happen? This amplitude is going to decay exponentially as the wave propagates in z direction. Yes or no? Okay, so if the amplitude of the wave is decaying, means this medium is offering some losses. This medium is offering some losses. So in case of lossy medium, alpha is not equivalent to 0. Alpha is not equivalent to 0. Right? Okay. Whereas if you consider lossless medium here, then in the lossless medium, the amplitude should not decay. Yes or no? Then only we can call the medium as what? Lossless medium. Right? So in a lossless medium, alpha is equal to 0. Whereas in case of lossless medium, lossy medium, alpha is not equivalent to 0. So you can make a note here. So alpha is equal to 0 in case of what? In case of lossless medium. In case of lossless medium. Whereas alpha is not equal to 0 in case of what? In case of lossy medium. In case of lossy medium. Right? Okay. Okay. Now first we are dealing with lossless medium. So in case of lossless medium here. So in case of lossless medium. In case of lossless medium, how the solutions are going to look like? So E bar of z comma t is equivalent to what? E into e power minus alpha z. Put alpha is equal to 0. In lossless medium, alpha is equal to 0. Put alpha is equal to 0, then amplitude is not going to decay exponentially. So you are going to get simply E into what? E into e power j of omega t minus beta z. Okay, so this represents the wave that is propagating in positive z direction. Similarly, if you want to represent the wave that is propagating in negative z direction, simply you have to put here plus sign. That's it. Right? Okay. Okay. So this is called as a complex solution. This is called as complex solution or complex representation of the field of an electromagnetic wave. Right? So similarly, you can represent for h bar of z comma t also. So h bar of z comma t is equivalent to what? H into e power j of what? Omega t minus beta z. So these are nothing but the complex solutions, we can say. Right? Okay. Okay. So whereas this E and H, in general, these are nothing but complex quantities. In general, this E and H are nothing but what? Complex quantities. Okay, so complex quantities means what here? See, E, I can write it as what? E is equal to some E naught into what? Into e power j phi. And H, I can represent it as H is equal to some H naught into e power j phi. So where this phi represents what? Where this phi represents initial phase here. Initial phase of the wave here, right? Okay, see, that means initial phase means at t is equal to 0. If we consider our starting point as t equal to 0 and z is equal to 0, right? If I consider this as our initial point, okay, so at the initial point z is equal to 0 and t equal to 0, right? So if you put z is equal to 0 and t is equal to 0, if the field is having some phase at that initial location, okay, so at the initial location, that is at z equal to 0 and at instant t equal to 0, if the field is having some initial phase phi, okay, then this amplitude will become what? Will become some complex quantity. So if the initial phase phi is equal to 0, so initially if there exists no initial phase, okay, then in that case at t is equal to 0, z equal to 0, this E will become what? This amplitude will become simply a real quantity. Okay, if there exists any initial phase, then this amplitudes will become what? Will become complex quantities. If there exists no initial phase, then this will become simply real quantities. Okay, generally in most of the cases we will consider the amplitudes as real quantities in general, in most of the cases. Okay, so there are situations where we can consider this initial phase also, right? Okay, yeah. So whenever if you consider this initial phase, if there exists any initial phase for the fields, then in that case this electric field and magnetic field amplitudes will become what? Will become complex quantities. Okay, yeah. So you have to keep this point in mind, right? Okay, right. Now if I want to write only the real time solutions, so in that case how the solutions are going to look like? So E bar of z comma t, I can write it as what? I can write it as simply E naught, some amplitude into what? Into, I can represent either in terms of what? Sine, or in terms of what? Or I can represent in terms of cos. Okay, so here E naught is a real quantity here. So in this case I can say these are nothing but what? These are nothing but real time solutions, right? So in this manner we can represent the real time solutions for the electric field and magnetic field. So for magnetic field you can represent in the same manner, that is H naught into sine of omega t minus beta z, or you can represent in terms of H naught into cos of omega t minus beta z. Okay, so here E naught is a real quantity, so these are called as what? These are called as real time solutions. So here also, depending upon the polarity before omega t and polarity before beta z, we can tell the direction of wave propagation, whether it is propagating in positive z or negative z, that we can tell based on the polarity before omega t and polarity before beta z. So if both are of opposite polarity, it is going to represent the wave propagating in positive z direction. Okay, that's what you have to keep in mind. If they are of opposite polarity, then it represents, if they are, what I am saying here, if the polarity before beta z and the polarity before omega t, if both are of opposite polarity, then it is going to represent the wave propagating in positive direction. If the polarity before beta z and the polarity before omega t, if both are of same polarity, then it is going to represent the wave propagating in negative direction. You have to keep this point in mind. So we always represent the fields of the electromagnetic wave either in terms of real time, or we can express in terms of what? Complex solution. Okay, so both are correct only. So it all depends upon our requirement. Wherever we need in this manner, we can represent here like this, or wherever we need as a real time solutions, there we can represent in this manner. Okay, so both are going to represent the wave that is propagating in a which medium here? Lossless medium. So in a lossless medium, the amplitude of the wave is not going to decay. So here alpha is equal to 0. There will be no attenuation of the wave in this lossless medium. Right? Okay? Okay. Right. Right. In this manner, we are going to represent the electric field and magnetic field in case of lossless medium. So similarly, if you consider lossy medium here, what is the only change here? Alpha will be present. That is, alpha is not equal to 0. Right? So in this case, how you can represent? E bar of z comma t is equivalent to what? Is equivalent to E into what? E power minus alpha z into e power j of omega t minus beta z. So this is the complex solution. So in terms of real time, how you can represent here? In terms of real time, you can represent it as what? E into e power minus alpha z into what? Into sine of what? Sine of omega t minus beta z, or in place of sine, you can represent in terms of what? Cos. So that is cos of omega t minus beta z. So this is a real time solution. In case of what? In case of lossy medium. In case of lossy medium, the amplitude has to decay exponentially, okay, as the wave propagates. Right? Okay. So this is how the solutions are in case of what? In case of lossy medium will look like. The only difference is alpha is present here, whereas here alpha will be equivalent to 0. That is the only difference between a lossless medium and lossy medium. Right? Okay. Okay. So in case of lossless medium, we are dealing with lossless medium here. So in case of lossless medium, right, alpha is equivalent to 0, and what is the condition for lossless medium? Epsilon r and mu r must be real, and conductivity of the medium is equivalent to 0. If it satisfies these two conditions, then only it is called as lossless medium. Right? Okay. So in a lossless medium, gamma is equal to what? Gamma is equal to alpha value is 0. Okay. So you are going to have only imaginary part, that is j into beta. So here alpha is equal to what? Alpha is equal to 0. Whereas beta is equivalent to omega into what? Omega into root over mu epsilon. If you observe here, this beta, that is phase constant, is depending upon the medium properties mu and epsilon. So that means if the medium changes here, this phase constant value is also going to change. Right? Whereas here in lossless medium, alpha is constant, that constant value is equivalent to 0. Right? Okay. Okay. So now see here. So the same thing I can represent here in this manner here. See, the phase velocity in a lossless medium is nothing but omega by beta. We can define it as ratio of what? Ratio of omega to beta. So here this is nothing but omega by, so beta is nothing but what? Omega into root over mu epsilon. So here omega will get cancelled. So the phase velocity expression in case of lossless medium is nothing but 1 by root over mu epsilon. Right? So I can write this phase velocity in this manner, that is 1 by square root of mu naught epsilon naught into mu r epsilon r. So 1 by square root of mu naught epsilon naught represents the velocity of the wave in free space, which is equivalent to the velocity of light in free space. Okay, so this will represent with CR. Okay, 1 by square root of mu naught epsilon naught will represent with C. So C divided by what? C divided by square root of mu r epsilon r. So this is the phase velocity expression of the wave in which medium? In lossless medium. In a lossless medium. So the units are nothing but meter per second. Right? Okay. Okay. So now see here. Now I can represent this beta as what? This beta is equivalent to. So this root over mu epsilon is nothing but what here? Root over mu epsilon I can write it as what? If you take root over mu epsilon to this side, I can write it as what? 1 by phase velocity. So that is nothing but omega by phase velocity. And what is this phase velocity? Phase velocity is nothing but c by root over mu r epsilon r. So if you substitute in case of phase velocity, if you substitute c by root over mu r epsilon r, what you are going to get? Beta. So I can express beta as omega by c into what? Root over mu r epsilon r. Okay, so in this manner we can remember the expression for beta. Okay, so as the medium properties changes, okay, if mu r value, epsilon r value changes, then beta value is also going to change, right? That's what you have to keep in mind. Okay, okay, right. And here we are having another expression, that is beta is equivalent to 2 pi by what? 2 pi by lambda. So that is radian per meter. 2 pi by lambda radian per meter. We can express beta as 2 pi by lambda also. See here, so beta is equivalent to what? So if I multiply with f in the numerator and denominator, 2 pi into f is nothing but what? Omega divided by lambda into f represents what? Velocity of the wave. So velocity of the wave we are calling it as phase velocity. So omega divided by what? Phase velocity. Right? If I multiply with f and f in the numerator and denominator, then I can represent this beta as what? Omega by phase velocity. So omega by phase velocity is also nothing but what? Beta. Okay. Oh, so here frequency, if I cancel that, then I can express beta as what? 2 pi by lambda. Right? Okay. Okay. So this is how we can represent beta in different manners, but all these expressions mean the same here. Okay, whether you represent in this manner or in this manner or in this manner, all are going to be what? All are going to be same, right? Okay. Okay, now one more thing here. One more thing here. Now see, beta is equivalent to omega by c into root over mu r epsilon r. Now here this omega is nothing but what? 2 pi into f. Okay, so this I can write it as 2 pi divided by c by f into root over what? Root over mu r epsilon r. Okay, so we know that lambda into f is equivalent to what? Is equivalent to c, right? So this is in free space here. In free space epsilon r equal to 1, mu r equal to 1. So epsilon is equivalent to epsilon naught, mu is equivalent to what? Mu naught. So in free space the velocity of the wave is nothing but the velocity of light. Okay, so this we can represent as lambda into f. So since it is a free space wavelength, I am representing this with lambda naught. So lambda naught represents free space wavelength here. I am representing it as a free space wavelength. Lambda naught into f is equivalent to c, right? Okay, so therefore c by f, therefore from here c by f is equivalent to what? Is equivalent to lambda naught. Okay, so here c by f I can represent as what? Lambda naught. So this is equivalent to, beta is equivalent to 2 pi by lambda naught into what? Root over mu r epsilon r, right? Okay, and we have seen that beta I can express it as what? Simply 2 pi by lambda. So this is equivalent to what you are going to get? 2 pi by lambda naught. If I take this root over mu r epsilon r to the denominator, I can write in this manner, that is lambda naught by root over mu r epsilon r. Okay, so which means if you compare these two, what you are going to get? Lambda is equivalent to what? Lambda is equivalent to lambda naught into root over mu r epsilon r. So that means if you change the medium here, not only beta is changing, but also what? But also lambda value is also going to change. Yes or no? Okay, so whenever the medium properties changes, beta value is going to change, and also lambda is also going to change, right? Okay. Okay, and one more thing, the phase velocity is equivalent to lambda into f where lambda is equal to what? Where lambda is equal to lambda naught by root over mu r epsilon r, right? Where lambda naught is nothing but what here? C by F. Okay, you have to keep all these points in mind, right? Okay, so this is the expression for phase velocity, lambda into F. So where lambda is nothing but lambda naught by root over mu r epsilon r, right? So which means as the medium changes, this phase velocity is also going to change or not? Yes or no here? Okay, after all, lambda is nothing but lambda naught by root over mu r epsilon r, right? Okay, so which means lambda value is also going to change as the medium changes. So as the medium changes, what are the parameters that are going to change? Beta has to change, and then lambda value has to change, and then phase velocity has to change, right? But what happens to frequency here? Frequency is not going to change. Frequency is not going to change, right? Okay, so frequency will remain same here. So that is frequency F is equal to what? Vp by lambda. So this must be what? This must be constant irrespective of what? Irrespective of medium, right? If you want, you can write this Vp as what? C by root over mu r epsilon r. This lambda you can write it as what? Lambda naught by root over mu r epsilon r. So here root over mu r epsilon r, here root over mu r epsilon r will get what? Cancel. So that means, which means frequency is independent of what? Is independent of medium parameters. Okay, so what is the conclusion we can make here is as the wave propagates from one medium to another medium, or if the medium properties are changing, then what are the parameters that are going to change? Beta is going to change, lambda is going to change, and the velocity of the wave is also going to change, whereas the frequency will remain what? The frequency of the wave will remain same. So these are the important conclusions that you have to understand from this, right? Okay, okay, I hope this is crystal clear here. So as the medium properties changes, as medium changes here, as medium changes, what are the parameters that are going to change? What are the parameters that are going to change as a medium changes? So beta is going to change, beta is going to change, and then lambda is also going to change, and then what? And then phase velocity of the wave is also going to change, whereas frequency is not going to change, is not going to change. Frequency of the wave will remain what? Will remain same. Okay, as you move from one medium to another medium, so these parameters are going to change, whereas the frequency of the wave is not going to change. So these are very, very important observations here. These are going to be helpful whenever we are dealing with as the wave propagates from one medium to another medium, what are the parameters that are going to change? If you are familiar with these things, then it is going to be very simple for us, right? Okay, okay. So next, so remember, next, see, we are dealing with lossless medium only. We are dealing with lossless medium only still, right? Okay, okay. So we can define another parameter which is called as a intrinsic impedance of the medium here. Intrinsic impedance of the medium. So the intrinsic impedance of the medium, we can get this intrinsic impedance by taking the ratio of what? Electric field to magnetic field. If you take the ratio of electric field to magnetic field of an electromagnetic wave, then you are going to get the expression for what? Intrinsic impedance of the wave, right? So this is equivalent to the expression for this one. In case of lossless medium, you can represent it as what? Square root of mu by epsilon. So which is equivalent to square root of what? Square root of mu naught by epsilon naught into what? Mu r by epsilon r. We know that this mu naught value is nothing but 4 pi into 10 to the power of minus 7, and this epsilon naught value is nothing but what? 1 by 36 pi into 10 to the power of minus 9. So if you substitute this, you are going to get this as 120 pi into what? Root over mu r by epsilon r. So this is the expression for intrinsic impedance of the medium. See, the units of electric field is volt per meter and the units of magnetic field is ampere per meter. So here meter will get cancelled. Volt per ampere is nothing but ohms. Okay, so that's why the units of intrinsic impedance, is nothing but what? Is nothing but ohms, right? And the expression for this one is a root over mu r epsilon r, right? Now, if you consider free space here, so in free space, what is the condition? Mu r equal to 1 and epsilon r will be equivalent to 1. So for free space, what is the intrinsic impedance here? What is the intrinsic impedance? Eta is equivalent to what? Eta is equivalent to 120 pi ohms. Yes or no? So generally we will represent for free space, I will represent the intrinsic impedance with eta naught. So eta naught value is how much here? 120 pi ohms for free space, right? Okay, for any other lossless medium, we can express eta as what? So in place of 120 pi, I am replacing with eta naught into what? Root over mu r by epsilon r, where this 120 pi is nothing but eta naught. Okay, for any other lossless medium, we can express the intrinsic impedance as what? Eta naught into root over mu r by epsilon r. So if you observe here, this intrinsic impedance parameter is also depending upon what? Is also depending upon the medium properties. Yes or no? Okay, so it is depending upon the medium properties. So as the medium changes, these medium properties are also going to change, and hence intrinsic impedance is also going to change. So we can include here, intrinsic impedance also, right? So as medium changes, eta is also going to what? Is also going to change. So these are the conclusions we can make here. See, if you make these observations, then it is going to be very simple for you to answer any question here, right? Okay. So as the medium changes, what are the parameters that are going to change? Beta is going to change, lambda is going to change, phase velocity is going to change, and intrinsic impedance of the medium is also going to change. So what is the parameter that is not going to change? That is nothing but frequency of the wave is not going to change, right? Okay. Yes, Bhaskar, fine Bhaskar, I am fine, right? Okay. So I hope these points are crystal clear, right? Okay. Now, based on this, we try to solve one problem here, right? Okay. Now, let us take air medium. Right? So if I consider air medium, so in air medium, mu r value is equal to 1 and epsilon r value is also equal to 1, right? So in this air medium, I am giving the expression for electric field. Let us say E bar of z comma t is equivalent to 120 pi into cos of 3 into 10 power 8 t minus 1 into z ax cap volt per meter. See, one more point you have to always keep in mind, that this electric field and magnetic field, are mutually perpendicular to one another, and also these two are mutually perpendicular to what? Mutually perpendicular to direction of what? Direction of wave propagation, right? Okay, so the electric field and magnetic field must be mutually perpendicular to one another, and also they must be perpendicular to the direction of wave propagation. Okay, and the plane in which this electric field and magnetic field are going to lie is called as what here? Transverse plane. So see here, if the wave is propagating like this, let us say the wave is propagating like this, right? Okay, so if you consider a plane, I am considering a plane here. So this plane is what? This plane is perpendicular to the direction of wave propagation. So the wave is propagating in this direction. Let us say this is Z. Okay, the wave is propagating in Z direction. So if I consider the plane here, so which is perpendicular to what? Which is perpendicular to Z axis. So that means it represents what? It represents Z equal to constant plane, or I can call this as what? Or I can call this as XY plane, right? Or I can call this as XY plane, right? So this plane which is perpendicular to direction of wave propagation is called as what? Is called as transverse plane, right? So always remember that the electric field and magnetic field must always lie in this transverse plane here. Electric field and magnetic field must always lie in this transverse plane. Okay, and also spatially they must be what? They must be 90 degrees apart. In this transverse plane, how the electric field and magnetic field must be? They must be perpendicular to one another. They must be perpendicular to one another in this transverse plane, right? Okay, and the wave direction propagation is perpendicular to what? Is perpendicular to this transverse plane, which means this electric field, the magnetic field are perpendicular to one another, and also these are perpendicular to what? These are perpendicular to the direction of wave propagation, right? And how this electric field and magnetic field are going to lie in the transverse plane? So they are going to lie in the transverse plane such that if you do AE cap cross AH cap, AE cap cross AH cap. So AE cap represents the direction of electric field in the transverse plane, and AH cap represents the direction of magnetic field in the transverse plane. Okay, so if you do cross product between AE cap and AH cap, it has to point in which direction? It has to point along propagation direction. Okay, see the directions we always represent with the help of what? With the help of unit vectors. So unit vectors will always gives the direction. Okay, okay. So here this is the direction of electric field. This is the direction of electric field, and this represents the direction of what? Direction of magnetic field, right? And this represents what? This represents direction of what? Direction of wave propagation. Wave propagation. Okay, so if you do the cross product between the direction of electric field to direction of magnetic field, then it has to point in the direction of wave propagation. Okay, so that means if you curl your right hand four fingers from the direction of E bar to the direction of H bar, then the right hand thumb has to point along the direction of wave propagation. Okay, so that means if the electric field is lying like this, okay, if the electric field is lying like this, so then the magnetic field has to lie like this, right? So if you do E bar cross H bar here, so this E field and H field has to lie in this transverse plane. So this is the transverse plane. Okay, if you do E bar cross H bar, okay, if you curl your right hand four fingers from electric field direction to magnetic field direction, then the thumb has to point, along what? Along the direction of what? Along the direction of wave propagation. So in this manner, the electric field and magnetic field has to exist in the transverse plane, right? Okay, okay. So is this point clear? Tell me, is this point clear? So always the electric field and magnetic field has to lie in the transverse plane, such that if you do E bar cross H bar, it has to point along the direction of wave propagation, right? Okay, okay. So that is, if you do the cross product between the direction of electric field and magnetic field, it has to point along the direction of wave propagation, right? Okay, so this is very, very important characteristic of an electromagnetic wave. Whether it is one-dimensional wave, two-dimensional wave, or three-dimensional wave, this property must be always followed. So that is electric field, magnetic field and the direction of wave propagation. Three must be mutually perpendicular to one another, and this electric field and magnetic field are going to lie in a plane which is called as transverse plane. This transverse plane must be always perpendicular to the direction of wave propagation, and in this transverse plane the electric field and magnetic field has to lie such that if you do E bar cross H bar, it has to point along the propagation of wave direction. Okay, so these points must be crystal clear here. Okay, so 1 minute here, I forgot to bring the water bottle. 1 minute. Right? Okay. So here coming to the problem, I have given the electric field as a function of z comma t. So which means you have to understand that this wave represents a one-dimensional wave, and the wave is propagating in z direction. You don't know whether it is propagating in positive z or negative z. Okay, but from the given expression we can tell whether it is propagating in positive z or negative z. So observe the phase of the wave. So this is nothing but omega, this is nothing but t. So omega t minus what? Minus beta z. So here beta value is nothing but what? Beta value is nothing but 1 here, right? Okay, so it is just like omega t minus beta z. So observe the polarity before beta z and observe the polarity before omega t. Both are of opposite polarity, hence we can say that the wave is propagating in positive z direction. Okay, the wave is propagating in positive z direction, and the electric field is pointing along which direction? It is pointing along x direction. So AE cap, so we know that AE cap cross AH cap must be equivalent to what? Must be equivalent to AP cap. So here AE cap is nothing but what? AE cap is nothing but AX cap cross. Okay, what is AH cap here? You don't know. You don't know AH cap, right? Okay, the direction of magnetic field, but you know the direction of wave propagation. What is the direction of wave propagation? Is positive z direction. So that means this must be AZ cap. So now you can easily determine the direction of what? AH cap. So what you have to put here so that you are going to get here AZ cap. See, AX cap cross AY cap is nothing but what? AZ cap. So which means here this AH cap is nothing but what? Is nothing but AY cap. So which means the magnetic field must be what? The magnetic field must point in y direction. That's what you can confirm here, right? Okay, so from this given electric field expression we can write its corresponding magnetic field expression. So how you can write? Tell me. So h bar of z comma t is equivalent to, so one thing is confirmed, that is it has to point, the magnetic field has to point in which direction? AY cap direction. So ampere per meter, right? Okay. So next how to write this remaining expression? See here we know that E by H is equivalent to what? Is equivalent to eta. Okay, here I have given the medium as air medium. So air medium or free space or vacuum all mean same here. All mean you are going to consider as same. Okay, so which means in air medium mu r value is equivalent to 1 and epsilon r value is also equivalent to 1. So in this air medium intrinsic impedance will become what? Eta naught, which is equivalent to what? 120 pi. So from here what is H here? H is equivalent to E by what? E by eta naught. Okay, so what is E? What is E here? E is nothing but 120 pi into cos of omega t minus beta z. So this divided by what? This divided by 120 pi. Okay, I have written already direction here. Now I have to return this magnitude part, that's it. Okay, so here you have to write E by eta naught. So this is nothing but E value. right? So this divided by eta naught is 120 pi. So if you substitute 120 pi will get cancelled. You are going to get the amplitude as 1 into what? Into cos of what? Cos of 3 into 10 power 8t minus what? Minus 1 into z, right? Okay, so this is how you can write. If they have given the electric field, this is how you can write what? You can write its corresponding magnetic field, right? Okay, okay. So always follow this one here, then you can easily write the direction of magnetic field. And if you want this magnitude, then you have to take the ratio of E by H, which is equivalent to eta. So if you want the expression for H, you can write it as what? E by eta. So remember here you have to write only the magnitude. So the direction of the field you are going to get from this expression, right? Okay, okay. So remember that one here, right? So in air medium, these are the expressions for electric field and magnetic field I have given. So these are the expressions I have given in air medium, right? Okay. So here I have told whenever they have given electric field, how to represent its corresponding magnetic field. I have told that one, right? Okay. Next. Now here, suppose in this air medium, now let us assume heavy rain is falling. Okay, so due to heavy rain here, due to heavy rain, what will happen here? The medium characteristics are going to change or not? So previously it is just like a air medium. Now because of heavy rain, you are going to have the water molecules also in the medium. Yes or no? Which means it is going to change the properties of the medium. So due to heavy rain, let us assume epsilon r value, that is the relative permittivity value, has changed from 1 to 9. Let us assume it has changed from 1 to 9. And mu r value, the medium property mu r value has changed from 1 to 16. Let us assume. Okay, so due to heavy rain in this medium, epsilon r value has changed from 1 to 9 and mu r value has changed from 1 to 16. So assuming amplitude of electric field remains same, assuming amplitude of electric field remains same, write down the new expressions, for E field and H field, Okay, so previously it is purely air medium. So here in air medium they have given the expressions for electric field and magnetic field. So now due to heavy rain, the properties of the medium is changed, that is epsilon r value has changed from 1 to 9, whereas mu r value has changed from 1 to 16. So assuming that the amplitude of the electric field is remaining same, write down the new expressions for electric field and magnetic field. So here we know that whenever the medium properties changes what are the parameters that are going to change? Tell me. Whenever the medium properties changes, what are the parameters that are going to change? Beta value is going to change, lambda value is going to change, phase velocity is going to change, intrinsic impedance is going to change. What will remain same? Frequency will remain same. Understood? So all these parameters are going to change, whereas frequency will remain what? Will remain same. So we know this concept here. So according to this, we try to write the expressions for electric field. Now in the expression of electric field, here we are having omega. So this omega value is not going to change whenever the medium parameters are changing. So there will be no change in omega value. But here the beta value here is 1. But beta has to change whenever the medium properties are changing. Okay, so what is new beta value here? So beta value in case of heavy rain here, Okay, so in this medium, what is beta value you are going to get? So beta value is equivalent to what? Is equivalent to omega by c into what? Root over mu or epsilon r. Right. So omega is nothing but 3 into 10 power 8 and c value is also nothing but 3 into 10 power 8 root over mu r. Mu r has changed from 1 to 16. Right, mu r has changed from 1 to 16 and epsilon r has changed from 1 to 9. So that means mu r value here is nothing but 16, whereas epsilon r value here is nothing but 9. Okay, so this 2 will get cancelled. So you are going to get a square root of 16 into 9, that is 4 into 3, that is 12. Correct na? Okay. Right. So therefore, beta value is equivalent to what? Beta value is equivalent to 12 radian per meter. 12 radian per meter. Right. So now you can express the expression for electric field E bar of z comma t is equivalent to. They are saying that assume that the amplitude of electric field remains same. So which means the amplitude is 120 pi, it remains same. So into cos of what? Cos of frequency is not going to change, that is omega value is 3 into 10 power 8 t minus beta value has to change. Beta value has become what? 12. Okay. So you take care of these calculations here. Okay. So if there is any calculation mistake, you can do that. Okay, you can correct that. Okay, it is pointing in x cap direction. So this is the expression for electric field, right? So similarly, if you want to write the expression for magnetic field, h bar of z comma t. Okay, so this is equivalent to. Now here you have to write the amplitude, right? Then you are going to get what? Cos of what? Frequency will remain same, 3 into 10 power 8t minus beta value has become 12. So here it will become 12 z and it is pointing in which direction? Ay cap, ampere per meter. But here we don't know about the amplitude of magnetic field. They have said that assume the amplitude of electric field remains same, but they have not said anything about the amplitude of magnetic field. So what happens to the amplitude of magnetic field here? So we know that E by H ratio is equivalent to what? Is equivalent to intrinsic impedance eta, which is equivalent to what? Which is equivalent to 120 pi into square root of mu r by epsilon r. So the amplitude of electric field is nothing but 120 pi divided by what? The amplitude of magnetic field we don't know, so that I am representing with h, which is equivalent to what? 120 pi into square root of what? Mu r value is 16, epsilon r value is 9, right? Okay, so here 120 pi will get cancelled. So h, the amplitude of magnetic field, is equivalent to what? Square root of 9 divided by 16, which is equivalent to 3 by 4, which is equivalent to 0.75. Okay, so here the amplitude of magnetic field must be what? Is nothing but 0.75, right? Okay, so that is the amplitude. That is the amplitude of magnetic field. So in this manner we can write the expression for magnetic field also, right? Okay. Okay. So first you have to observe what are the parameters that are going to change as the medium properties changes. So from that you can easily write the expressions, right? Okay. So here beta is changing and the amplitude of magnetic field is also changing, right? Okay. Okay. Right. So I hope this is crystal clear here. I hope this is crystal clear. Right. Okay. So now here I will give you one more problem here. So that is I will give you the expression for electric field and you have to write the expression for what? Expression for magnetic field. Okay. So here I am considering the medium as free space. I am considering the medium as free space. Okay. In free space I am giving the expression for electric field. So E bar is equivalent to let us say some 10 into sine of what? Sine of omega t, sine of okay, sine of omega t minus beta z into ay cap ampere per meter. Okay, so write down its corresponding expression for magnetic field here. You have to write down the corresponding expression for magnetic field. Okay, so I have given the medium as what? Free space, right? So I have given the expression for electric field and I am asking the expression for magnetic field. Okay, so it is going to be very simple here. See here. So the direction of, we know that AE cap cross AH cap is equivalent to AP cap. The electric field is pointing in AY cap direction. You don't know the direction of magnetic field, and the wave is propagating in which direction? Positive Z direction. So that is AZ cap. So from here you can tell the direction of magnetic field. What is the direction of magnetic field? Tell me. See, always remember this one here. So AX cap, AY cap, AZ cap. Okay, so if you do AX cap cross AY cap, you have to get AZ cap. If you do AZ cap cross AX cap, you have to get AY cap, right? Okay, so if you move in reverse manner, then you have to get negative sign. So that is AY cap cross AX cap will be minus AZ cap. Okay, so that's how you can remember this table, right? Now see here, you have to get AZ cap. Here you have to get AZ cap. So if I do AY cap cross AX cap here, then you have to get minus AZ cap. But here you have to get a plus AZ cap. So which means here I have to do the cross product with minus AX cap. Which means the magnetic field has to point in which direction? It has to point in negative Z direction. So if I want to represent this electric field and magnetic field in the transverse plane here, in the transverse plane, how I can represent? So let us assume this is the transverse plane. Okay, transverse plane. So transverse plane is always perpendicular to what? Perpendicular to wave propagation direction. The wave is propagating in which direction? Z direction. So which means the transverse plane must be perpendicular to Z. So that means it must be XY plane. So this is a Z equal to constant plane or what? Or XY plane or XY plane. So XY plane means here I am considering this axis as X axis and I am considering this axis as Y axis. Okay, and the wave is propagating in which direction? We know that it has to propagate perpendicular to this transverse plane. Whether it has to propagate out of the transverse plane or it is propagating into the transverse plane. That is, out of the transverse plane is nothing but what? Positive Z here, and into the transverse plane is nothing but what? Negative Z. So here the wave is propagating in which direction? Positive Z direction. So here at the center of the transverse plane always represent the direction of what? Wave propagation. So here the direction of wave propagation is what? Is out of the port. It is pointing in positive Z direction. Right? Okay. Now the electric field is pointing in which direction? AY cap. So the electric field is pointing in AY cap direction. Positive AY cap direction. Okay, so this is the electric field. We know that if you do the cross product between E field and H field, the thumb has to point in the direction of wave propagation. Right hand thumb has to point in wave direction propagation. Okay, so if the electric field is pointing in positive Y direction, what must be the direction of magnetic field? Such that if you do E bar cross H bar, okay, the thumb has to point along the direction of wave propagation. So always at the center here represent the direction of what? Direction of wave propagation. Okay, now it is going to be crystal clear here. What must be the direction of magnetic field? Tell me, in this transverse plane, what must be the direction of magnetic field? Tell me here. What it must be? It has to lie in the along positive X direction or negative X direction? It has to lie along negative X direction. Yes or no? Now if you do E bar cross H bar, if you curl your right hand four fingers from E to H, the thumb is pointing along the direction of wave propagation. So in this manner, the electric field, magnetic field and the direction of wave propagation we have to represent. Right? Okay, I hope this point is crystal clear here. Right? Okay. Now this H field is equivalent to what? This H field is equivalent to what you are going to get, tell me? This H field is equivalent to, so it is pointing in which direction? Negative x direction. It has to point in negative x direction, and its units are nothing but what? Ampere per meter. So here I have written wrongly, the units here must be volt per meter. Here must be volt per meter, right? Okay, now you have to write this magnitude of H field. So what I have told you, so E by H is equivalent to what? Here we have considered the medium as what? Here we have considered the medium as free space. E by H is equivalent to eta naught. So H is equivalent to what? E by eta naught. So if you take this E by eta naught, what you are going to get? You are going to get 10 divided by eta naught into what? Sine of omega t minus beta z. So this is the expression for what? This is the expression for magnetic field, right? So in this manner you have to write the expression for magnetic field whenever they have given the expression for electric field. So similarly, in the same manner, if they have given the expression for magnetic field, then you can write the expression for electric field. Okay, so we will take one more case here. Okay, so that is if I consider H bar is equivalent to, see here, the electric field and magnetic field has to lie in the transverse plane. Okay, and the direction of wave propagation must be perpendicular to the transverse plane, right? Okay, such that if you do E bar cross H bar, then the thumb has to, right hand thumb has to point along the direction of wave propagation. I hope these things are crystal clear. Okay, okay. Now in the transverse plane, it is not compulsory that the electric field has to lie only along y direction, or it has to lie only along x direction. So it can lie anywhere in this transverse plane. The electric field can lie anywhere in this transverse plane, right? Such that always if you do E bar cross H bar, it has to point along the direction of wave propagation. That's it. Okay, so it can lie anywhere in the transverse plane. So if I consider this as the transverse plane, right? So let us say this is x axis and let us say this is y axis, and let us assume the wave is propagating out of the board, that is in positive z direction, right? Now if I consider electric field somewhere here, so now it is having both x component as well as what? Y component. Okay, now where must be H field present here? H field has to present in this transverse plane, and it must make 90 degrees spatially with respect to electric field, and if you do E bar cross H bar, it has to point along the direction of wave propagation. Okay, it has to make 90 degrees means it can lie either in this second quadrant or it can lie in this fourth quadrant. That is the only two options we are having. Yes or no? Okay, it can lie either in fourth quadrant or in second quadrant. If it lies in fourth quadrant, then if you do E bar cross H bar, the thumb is pointing into the board, but here the wave is propagating out of the board. Okay, so we can conclude that the magnetic field cannot lie in the fourth quadrant. So the magnetic field has to lie in this transverse plane, such that if you do E bar cross H bar, then the thumb has to point, right hand thumb has to point along the direction of wave propagation. Okay, so which means H bar cannot lie in the fourth quadrant. It has to lie in which quadrant here? It has to lie in the second quadrant like this, right? So this is nothing but H bar. So which means here, if the electric field is having a x component, it is having here x component, and it is having here y component, right? And this magnetic field is having which components here? It is having a negative x component, and it is having what? It is having a positive y component. It is having negative x component and it is having positive y component, right? So which means this x component of electric field, see, one component has to produce the other. Yes or no? Okay, so this x component of electric field is going to produce what? Is going to produce y component of what? Y component of magnetic field. Okay, because these field components must be what? Must be always mutually perpendicular to one another. So the x component of electric field is producing this y component of magnetic field, and this y component of electric field is producing what? Is producing negative x component of magnetic field. Okay, so one component is producing its corresponding orthogonal component, right? So Ex is producing y component. So if you do cross product between Ex and Hy, it is going to point in which direction? Positive z direction. Similarly, if you do the cross product between y component of electric field and negative x component of magnetic field, then the thumb is pointing in which direction? Along the direction of wave propagation, right? So which means here the x component of electric field is producing what? Y component of magnetic field, right? And the y component of magnetic field is producing what? Is producing negative x component, is producing negative x component of magnetic field, right? And vice versa. So you can tell in other manner also, that is negative x component of magnetic field is producing y component of electric field, or I can say the y component of magnetic field is producing what? Is producing x component of electric field. So one component is producing the other, right? Okay, okay. So now if suppose here I have given the expression for H field here, I have given the expression for H field. So H field is equivalent to some 5 into cos of omega t minus omega t plus beta y, omega t plus beta y, ax cap ampere per, so sorry, ax cap okay, minus 4 into sine of omega t plus beta y into what? Into az cap ampere per meter. Then if I ask you to write the corresponding components of electric field, if I ask you to write the corresponding component of electric field, okay, so how you can write here? Tell me how you can write. See the same thing here. So first let us consider the x component of magnetic field. So this is the x component of magnetic field and this is the z component of magnetic field. Okay, so this is magnitude of z component, and the z component is pointing in which direction? It is pointing in minus az cap direction. Okay, always you have to see the magnitude separately and direction separately, then you don't have any confusion. Okay, so here this is the magnitude, right, and the direction is along negative z direction. Okay, so here the wave is propagating in which direction here? The wave is propagating in negative y direction. So here the wave is propagating in negative y direction, Why it is propagating in negative y direction? Because the polarity before omega t and the polarity before beta y both are what? Both are of same polarity. So which means we can conclude that the wave is propagating in negative y direction. So if it is propagating in y direction, it may be positive y or negative y. Okay, what must be the transverse plane? Transverse plane must be y equal to constant plane. So y equal to constant plane means it represents what? Zx plane. So here you can draw Zx plane here. See why I am doing this analysis means it is going to be very much helpful here. This analysis, this type of analysis is going to be very much helpful in understanding the concepts. Okay, okay. So here let us say this is x and this is z. So this is Zx plane. Okay, so that is y equal to constant plane, right? And the wave is propagating in which direction? It is propagating in a negative y direction. So here negative y means how I have to represent? Tell me how I have to represent. See, if you do z cross x here, if you curl your right hand fingers from z to x, the thumb is going to point in positive y. So that means here positive y is pointing into the board, right? Which means negative y has to point out of the board. Okay, or you can take here z axis, or if you take here z axis and here x axis, then in that case if you do z bar cross x bar, positive y has to point out of the board and negative y has to point into the board. So it all depends upon how you are choosing, in which direction you are choosing x and in which direction you are choosing z, right? Okay, so both are going to give you whether you take in this manner or in this manner, both are going to give you finally the same result here. Okay, it doesn't matter. Okay, if I consider in this manner, then positive y is going to point into the board and negative y is going to point out of the board. So always at the center of the transverse plane, so this is the transverse plane, at the center of the transverse plane always represent the direction of wave propagation. So here this represents the direction of what? Direction of wave propagation. Okay, it is propagating in negative y direction here. Negative y is coming out of the board here, right? And here I have given the magnetic field. The magnetic field is having positive x component. It is having positive x component and negative z component. It is having positive x component and negative z component. So that means it is having positive x component and negative z component. That means the resultant magnetic field has to lie in the fourth quadrant like this. So this is the H field, right? So in which quadrant E field must lie here? See, E field and H field, the spatial phase shift must be 90 degrees. So it has to lie either in the first quadrant or it has to lie in the third quadrant. These are the two options you are having. Okay, if it lies in the first quadrant, then if you do E bar cross H bar, okay, then the thumb is pointing in which direction? Into the board. But here the wave is propagating in which direction? Out of the board. So electric field cannot lie in the first quadrant. It has to lie in which quadrant here? It has to lie in the third quadrant like this. So this is nothing but E bar. So now if you do E bar cross H bar, the thumb is pointing along the direction of wave propagation. So which means here the electric field is going to have which components? It is going to have which components here? It is having a negative z component, right? It is having negative z component, and it is having what? It is having a negative x component. It is having negative x component. Okay, and this H field is having which components? This H field is having a positive x component, and it is having a negative z component, right? Okay, so I can say that this negative x component of electric field is going to produce what? Is going to produce the negative z component of magnetic field, and this negative z component of electric field is going to produce what? Is going to produce the positive x component of what? Positive x component of magnetic field, or you can say vice versa. Okay, this is the conclusion we can make here. Okay, okay. So just we are analyzing with the help of transverse plane. So which components of fields are going to present and which components are not going to present. So that's what we are checking with the help of this transverse plane, right? Okay, okay. So we have concluded that if the magnetic field is having x component and negative z component, then the negative z component of magnetic field is going to produce negative x component of electric field, and this positive x component of magnetic field is going to produce what? Negative z component of electric field. So that means this E bar is going to have what? Is going to have positive x component. It is going to have positive x component and it is going to have negative x component and it is going to have negative z component. Okay, so it is going to have negative z component, right? Okay, okay. Yeah. So what is producing this x component of electric field here? What is producing this x component of electric field? Which component is producing? That is negative z component of magnetic field is producing, right? And this z component, this negative z component of electric field, which component of magnetic field is producing this one? So that is nothing but positive x component of magnetic field is producing this one, right? Okay, right? Okay. So here if you take the ratio of Ex to Hz. I am considering only magnitude here. If I write only Ex by Hz, I am not putting any bars here. Okay, so if I am simply writing in this manner, then you have to assume that this is the magnitude, this is also magnitude. Okay, so Ex by Hz will give you what? Will give you the intrinsic impedance of the medium, right? So similarly, if I take Ez by Hx, I am considering only magnitude. Okay, so this is going to give you what? This is going to give you intrinsic impedance of the medium, right? Okay, okay. So therefore, E bar is equivalent to what? E bar is equivalent to, so Ex is equivalent to what? Eta into Hz. So Ex, in place of Ex, I can write eta into what? Eta into Hz. So eta into Hz into what? Minus Ax cap plus what? Plus eta into Hx, into what? Into minus Az cap, right? Okay, so here Hz is nothing but what here? So this is Hx, right? And this is nothing but what? This is nothing but Hz. You should not include this minus sign here. So this is magnitude, this is direction, right? Okay, always see the magnitude separately and direction separately, right? So here Hz means 4 sine of omega t plus beta y. So here I can write, therefore electric field E bar is equivalent to what? Eta into Hz is nothing but what? Hz is nothing but 4 into sine of omega t plus beta y. Okay, so 4 into sine of omega t plus beta y. Okay, so this is Hz. So this multiplied by minus Ax cap, okay, plus eta into what? Eta into Hx. So what is Hx here? Hx is nothing but the magnitude of x component, that is 5 into cos of omega t plus beta y. So 5 into cos of omega t plus what? Plus beta y, right? Okay, so what is its direction? Its direction is negative z direction. So this is the expression for electric field here. So in this manner we can write. So with the help of transverse plane also we can write the expression. If they have given magnetic field, we can write the expression for electric field. Similarly, if they give the expression for electric field, we can write the expression for magnetic field. Okay, with the help of what? With the help of this transverse plane diagram, right? Okay, okay. Okay, so I hope this is also crystal clear here. I hope this point is also crystal clear, right? Is this clear here? Is this clear? Okay, okay. Right. Okay, so I will give finally the formula here. So that is, if they have given electric field and if they ask to determine H field, then how we can do that? If they have given H field and if they ask us to determine the electric field, then how we can do that? Okay, I will directly give you the formula. You can just remember this formula if you want. Okay, you can follow these procedures or you can directly apply this formula also. So that is, here H bar is equivalent to AP cap cross what? Cross E bar divided by eta. Okay, and if they have given H field and if you want to determine the electric field, then E bar is equivalent to eta into H bar cross what? Cross AP cap. Okay, so in this manner we can directly determine the expression for electric field and the expression for magnetic field. Okay, okay. So where this AP cap is nothing but what? AP cap is nothing but the unit vector along direction of wave propagation, okay, okay. So in this manner you can directly write the expression for electric field if they have given magnetic field, or if they have given electric field and if they ask to write the expression for magnetic field, you can use this formula. Okay, so you can remember these two formulas here, right? If you want, you can determine for this question here, for this question by using the formula, you can determine its corresponding electric field. Okay, you are going to get what? You are going to get the same expression. You are going to get the same expression, right? If you want, you can check that, right? Okay, so I have told the analysis, and also I have given the formula. Okay, so if you forget formula, if you are confused with the formula, then if you go to the basics, that is analysis, okay, then you can easily answer this type of questions. See, this type of questions we can expect not only in lossless medium, throughout the subject here, this is going to be very much helpful. So that's why I have given this analysis here. Okay, so transverse plane and the wave propagation must be always perpendicular to the transverse plane. So all these things must be crystal clear. Okay, so throughout our subject, these concepts will follow, right? Okay, so I hope all these things are crystal clear, right? Okay, so now we will take a lunch break here. We will take lunch break. So we will take a lunch break here, right? We will take lunch break. So now the time is 1:50. Okay, so 1:50 p.m. to 2:50 p.m. So 1 hour lunch break here. Okay, then we'll start our class at 2:50 p.m. Start at 2:50 p.m. Okay, okay. So I hope all the things are crystal clear. So now we'll take lunch break, and we'll meet again at 2:50 p.m. 2:50 p.m. right? Okay. Okay. So okay, then we'll meet at 2:50 p.m. So until then, have some lunch break. We'll meet again at 2:50 p.m. Okay. So okay, I think all the things are crystal clear. Funny Krish, it is not possible to complete within one single session here. I'll plan to take 1 or 2 more sessions also. Okay. Okay. Right. Okay, yeah. So okay, then take the lunch break. So we'll meet after the lunch break. So until then, take care. Bye bye. Hello. Okay. So welcome back all of you, right? So this 1 hour break is completed. So we have taken from 1:50 to 1:50 p.m. to 2:50 p.m. right? Okay. So first of all, confirm whether my audio and video is clear or not. Tell me here. So let me know whether audio and video are clear or not. So if you confirm this, we can start our lecture. So please give some comment in chat box whether audio and video everything is clear or not. So if you confirm this, we will start our session. Right? Okay. So I hope audio and video everything is clear, right? Okay. Okay. So we have studied we are studying about this lossless medium, right? Okay. So the condition for lossless medium is conductivity is equivalent to 0, epsilon r and mu r values must be real quantities. So if it satisfies these two conditions, then it is going to behave as lossless medium, right? So in this lossless medium, so we have seen gamma is equal to what? Gamma is equal to z beta. So here alpha is equal to 0, where beta is equal to omega into root over mu epsilon, or we can write the same thing as omega by c into root over mu r epsilon r, or we can write the same thing as 2 pi by lambda, right? Okay. And phase velocity is equivalent to what? Is equivalent to omega by beta, right? Next, we have determined the expression for eta. Okay, so this omega by beta, what we got? C by root over what? Root over mu r epsilon r, right? And then intrinsic impedance eta is nothing but the ratio of E by H, which is equivalent to what? Which is equivalent to eta naught into root over mu r by epsilon r. Okay, and also we have seen that the wavelength of any medium is equivalent to lambda naught by root over mu r epsilon r. Okay, so these are the things that we have seen in case of lossless medium. And also we have studied if they have given the electric field, okay, then how to determine its corresponding magnetic field. So that is, magnetic field is equivalent to AP cap cross E bar divided by what? Eta. Okay, so similarly, if they given H field and ask us to determine the electric field, so we have seen that E bar is equivalent to eta into H bar cross what? Cross AP cap, right? Okay, so these things we have seen here, right? Okay, and here coming to intrinsic impedance expression. Coming to intrinsic impedance expression, so this is eta is equal to E by H, which is equivalent to eta naught into square root of what? Mu r by epsilon r. So this eta naught value is nothing but what? 120 pi. 120 pi. So this 120 pi is a real quantity, and in case of lossless medium, this mu r value is real, epsilon r is also real. So this overall eta is what? Is a real quantity. It is a real quantity. So in case of what? Lossless medium. So if it is a real quantity means what here? Eta is equivalent to E by H, which is equivalent to 120 pi into root over mu r by epsilon r. So it is a real quantity means it is having magnitude, and what is the phase shift here? Phase shift here is nothing but what? Is nothing but 0 degrees. Yes or no? So if you are having some complex quantity, then you are going to have both magnitude as well as phase shift. If you are having some positive real quantity like this, then the phase shift I can express it as what? Simply 0 degrees. Okay, so this 0 degrees represents the time phase shift between the electric field and magnetic field of an electromagnetic wave. Okay, so this 0 degrees represents what here? This 0 degrees represents time phase shift here. This represents time phase shift. Time phase shift between what? Between E and H fields. Between E and H fields of an electromagnetic wave. Okay, so this is in case of what? This is in case of lossless medium. So I can say that in a lossless medium, okay, the intrinsic impedance is a real quantity and the time phase shift here is 0 degrees. So this time phase shift represents time phase shift between what? Electric field and magnetic field. Remember that spatially the electric field and magnetic field are 90 degrees apart. Okay, but here I am saying this is the time phase shift. This is not the spatial phase shift. This is the time phase shift between electric field and magnetic field. So electric field and magnetic field, between electric field and magnetic field, the time phase shift is 0 degrees in case of lossless medium, which means if you consider an electromagnetic wave, you are going to have oscillating electric field and oscillating magnetic field in the transverse plane. Right. So this oscillating electric and magnetic field are going to be in time phase here, which means whenever this electric field makes minima, at the same time the magnetic field will also makes minima, and whenever the electric field makes maximum, at the same time the magnetic field will also makes maximum. So this electric and magnetic fields are going to make their minima and maxima at the same time. Okay, then we can say that this electric field and magnetic field are in what? Are in time phase. Okay, so what we can conclude here is E and H fields are in what? Are in time phase. Okay, so that is the phase shift is 0 degrees between E and H field. Okay, so this is in case of what? This is in case of lossless medium. Right? Okay. Next, so this is all about lossless medium. So next we'll go for a lossy medium here. We'll analyze for lossy medium. Okay, so lossy medium, so this is or I can say medium with a finite conductivity. So that is sigma is not equal to 0 here. So I have told that if sigma is not equal to 0, then the medium is going to behave as what? Lossy medium. What is the condition for lossless medium? The condition for lossless medium is sigma must be equal to 0, and at the same time epsilon r and mu r values must also be what? Real quantities. So if it satisfies these two conditions, then only it is going to behave as lossless medium. If any of these conditions fails, then it is going to behave as what? Then it is going to behave as lossy medium. Okay, even one condition fails, then also it is going to behave as what? Lossy medium. Okay. So here if I assume the medium as a if I assume that the medium is having some finite conductivity, so that is sigma is not equal to 0, in that case this medium is going to behave as what? Lossy medium. So lossy medium means in this medium the attenuation constant is not equivalent to 0. You are going to have the attenuation of the wave as the wave propagates in this medium. Okay, so why we are going to have the attenuation, all those things we will see as we proceed here. Right? Okay. So in this lossy medium, so first of all we will see what is the propagation constant. So the propagation constant gamma is a complex quantity. So this is equivalent to, here in a lossy medium you are going to get the expression for propagation constant as a root over j omega mu into what, sigma plus j omega epsilon. So this is the expression you are going to get for gamma in case of what, in case of lossy medium, right? Okay, so if you observe here, this is a complex quantity. This gamma we are getting here as a complex quantity. So if it is a complex quantity means it is going to have what, real part as well as what, imaginary part. So this complex quantity, you can simplify this and you can represent the real part separately and you can represent the imaginary part separately, right? So this complex quantity is going to have a real part as well as imaginary part, right? So the real part of gamma we call it as attenuation constant and the imaginary part of gamma we call it as what, phase constant. So the definitions of gamma, alpha and beta already we have defined. Okay, the same definitions are valid here also, right? Okay, okay. So if you simplify this one here, if you simplify this expression and try to write this expression in terms of what, in terms of real term and imaginary term, that is in terms of alpha and beta, okay, what you are going to get. So I am not doing that mathematical calculations and all, so I am giving directly, if you separate the real part and imaginary part, so finally what is the expression you are going to get for alpha and what is the expression that you are going to get for beta. So that's what I am going to give now. Okay, so the expression for alpha here, in case of, now we are dealing with lossy medium, okay, remember that point, right? Okay, so the expression for alpha you are going to get as omega into root over mu epsilon by 2, omega into root over mu epsilon by 2 into square root of 1 plus sigma by omega epsilon whole square minus 1 whole to the power of 1 by 2, whole to the power of 1 by 2. So the units of alpha is nothing but what, Nepper per meter, right? Similarly, we are going to get the expression for beta, that is phase constant, is equivalent to omega into what, omega into root over mu epsilon by 2 into square root of 1 plus sigma by omega epsilon, 1 plus sigma by omega epsilon whole square plus 1 whole to the power of what, 1 by 2. The units are nothing but radian per meter, radian per meter. So these are the expressions for alpha and beta that you are going to get in case of what, in case of lossy medium, in case of lossy medium. Okay, okay. So this is actually the expression for propagation constant in case of lossy medium. So if you simplify this one and if you separate the real part, you are going to get the expression for alpha, and if you write the imaginary part, you are going to get the expression for beta. So I have given, without doing that mathematical calculations and all, so I have given the expressions for alpha and beta. If you separate the real part, this is the expression you are going to get, and if you separate the imaginary part, this is the expression you are going to get. Now if you observe here, both the expressions are looking in the same manner, right? So here you are having omega into root over mu epsilon by 2, here also you are having the same thing, and here under root you are having 1 plus sigma by omega epsilon whole square, here also you are having the same thing, and here you are having minus 1 whole to the power of 1 by 2, but here you are having what, plus 1 whole to the power of 1 by 2. So the only difference here is here you are having minus sign and here you are having plus sign. So apart from this everything is going to be same. Understood? Okay, so even if you get some confusion, where you must have minus sign and where you must have positive sign, okay, that also you can easily check here. Because see here, for a lossless medium, what is the condition? So the conductivity of a lossless medium must be equivalent to 0, right? Okay, and attenuation constant alpha must also be equal to 0 in case of lossless medium. So if you put sigma equal to 0 here, then what you are going to get? If you put sigma is equal to 0, that is the condition for lossless medium. If you put sigma equal to 0 here, this term will become 0, right? Then root over 1 is nothing but 1. So 1 minus 1 will become 0. right? So that means alpha you are getting what? 0. Right, that is the expression for what? That is the value of alpha in case of what? Lossless medium. So whenever you put sigma equal to 0, you are getting the expression for alpha in lossless medium. Yes or no? And similarly here, if you put sigma equal to 0, right, then what you are going to get? Square root of 1, that is 1. 1 plus 1 is 2. It is under root. Okay, so that means here you are going to get root 2. So here root 2, here root 2 will get cancelled. You are going to get expression for what? Expression for beta as omega into root over mu epsilon, which is same as what? Which is same as beta for lossless medium. Yes or no? Okay, so just by replacing sigma equal to 0, you can check whether you are getting the expression for alpha as 0 and you are getting the expression for beta as omega into root over mu epsilon or not. So in this manner you can check the expressions for alpha and beta. Okay, okay. So if you substitute sigma equal to 0, then you have to get the expressions of alpha and beta for lossless medium. Okay, okay. So I hope this point is crystal clear, right? Okay, okay. Next, see here. Okay. Next, the intrinsic impedance. The intrinsic impedance of this lossy medium. Okay, the intrinsic impedance for the lossy medium is equivalent to. So you have to take the ratio of what? E to H. You have to take the ratio of E to H. Okay, I am not doing this derivation here, so I am just giving the expression for this intrinsic impedance in case of what? Lossy medium. So what is the expression you are going to get? You are going to get square root of what? Square root of j omega mu divided by sigma plus j omega epsilon. Okay, so this is the expression you are going to get for intrinsic impedance in case of what? Lossy medium. Right, now here if you observe here, this E by H ratio you are getting as some complex quantity. This is some complex quantity, isn't it? Okay, so if it is some complex quantity means it is going to have both. It is going to have both magnitude as well as what? As well as phase shift. As well as phase shift. Okay, so this phase shift represents what? This phase shift represents time phase shift. This represents time phase shift between what? Between E and H fields. E and H fields. Right? Okay. Okay. Yeah. So which means in case of lossy medium, okay, E by H ratio is a complex quantity, which means it is going to have both magnitude as well as what? Phase shift. So that means there exists some time phase shift between the electric field and magnetic field in case of what? In case of lossy medium. Whereas in case of lossless medium, there exists no time phase shift between electric field and magnetic field. So these are the differences that you have to observe between lossless medium and lossy medium here. Okay, in case of lossless medium, electric field and magnetic field are in time phase, whereas in case of lossy medium, the electric field and magnetic field, there exists some time phase shift between electric field and magnetic field. Okay, now what is the magnitude of eta loss here? What is the magnitude you are going to get? See, eta lossy is going to have some magnitude as well as it is going to have some phase shift. Right? Okay, so here I am representing this as phi lossy. Right? It is having both magnitude as well as what? As well as some phase shift. So what is the magnitude you are going to have? Tell me. So the magnitude of eta lossy is equivalent to what? Is equivalent to. So what is the magnitude of this quantity here? Tell me. So here I can write this as square root of the magnitude of numerator is nothing but omega mu divided by what is the magnitude of denominator here? The magnitude of denominator is nothing but square root of sigma square plus what? Plus omega epsilon whole square. This is the magnitude of the denominator. This is the magnitude of the numerator. right? Okay, so this is equivalent to, I can simplify this further. So that is, I can write this as square root of omega mu divided by, so if I take omega epsilon outside here, outside this root, okay, so omega epsilon whole square, if I take outside this root, what you are going to get? You are going to get omega epsilon into square root of what? Into square root of sigma by omega epsilon whole square plus 1. So this is what you are going to get if you take omega epsilon whole square outside this root. Okay, now if you observe here omega will get cancelled, so you are going to get the magnitude of eta lossy. The magnitude of eta lossy is equivalent to what? Is equivalent to what you are going to get? Square root of mu by epsilon. So divided by what? Divided by sigma by 1 plus sigma by omega epsilon whole square, whole to the power of what? Whole to the power of. So here you are having root, and again here you are having another root. So that is whole to the power of 1 by 4. Right? Okay. Okay. So this is the magnitude. This is the magnitude of eta lossy. And what is this square root of mu by epsilon here? So we know that this square root of mu by epsilon is the expression for the intrinsic impedance in case of what? Lossless medium. Right? So that means you can replace this with what? Simply eta. So where eta is equivalent to what? Where eta is equivalent to square root of mu by epsilon ohms. Right? Okay. Okay. So therefore magnitude of eta lossy here, magnitude of eta lossy, I can write it as what? Simply eta divided by what? Divided by 1 plus sigma by omega epsilon whole square, whole to the power of what? Whole to the power of 1 by 4. So this is the expression for magnitude of eta lossy. Okay. So where eta is nothing but what? Where eta is nothing but square root of mu by epsilon. Where eta is nothing but square root of mu by epsilon. Right? Okay. So this is the magnitude. Right. So now what is the time phase shift between electric field and magnetic field? So that is nothing but what? That is nothing but phi lossy. Right? So you have to determine the phase of this complex quantity here. How you can determine the phase here? Tell me. So here you are having eta lossy is equivalent to square root of j omega mu divided by sigma plus j omega epsilon. Right? So I want to determine phi lossy here, phi lossy. So that is phase shift. This is the time phase shift between electric field and magnetic field in case of what? Lossy medium. So phi lossy is equivalent to, so I am taking the root, right? So I have to consider the phase of the numerator and the phase of the denominator. So what is the phase of the numerator here? It is having only imaginary part. Yes or no? So that means the phase shift of this numerator is nothing but what? Is nothing but 90 degrees. Yes or no here? So here you are having simply plus j here. Plus j means what? Plus j means you can write it as what? E power j 90. Okay, so which means this represents the phase shift of what? 90 degrees. So in the numerator you are having the phase shift of 90 degrees. So divided by what is the phase shift of this denominator here? So I can write this phase shift as a tan inverse of what? Tan inverse of imaginary part by real part. So that is omega epsilon by sigma. In this manner I can write. Okay, so this is equivalent to square root of what? Square root of 90 degrees. If I take this phase to the numerator, what I can do? I can subtract this phase if I take it to the numerator. So 90 degrees minus tan inverse of what? Tan inverse of omega epsilon by sigma. So in this manner I can represent. Okay, now if you take this total angle outside the root here, outside the root, okay, then how you can represent? What you have to do? So whenever you are taking the angle out of the root, you have to divide that angle by what? By 2. Yes or no here? Okay. Okay. So that means finally what you are going to get? Phi lossy is equivalent to. So from this expression, so what you can write? Take that angle out of what? Out of the root. So out of the root means you have to divide the total angle by 2. So 90 by 2 is 45 degrees minus tan inverse of what? Tan inverse of omega epsilon by sigma divided by what? Divided by 2. So this is the phase shift here. This is the phase shift that you are going to get. So this is the time phase shift between electric field and magnetic field in case of what? In case of lossy medium, right? Okay. So I hope this point is also crystal clear, right? So we got the expression for magnitude of eta lossy. What is the expression for magnitude of eta lossy we got? Is nothing but eta divided by 1 plus sigma by omega epsilon whole square whole to the power of what? Whole to the power of 1 by 4, and we got the expression for phi lossy. So that is equivalent to 45 degrees minus tan inverse of what? Tan inverse of omega epsilon by sigma divided by 2. So this is the phase shift. Okay. Okay. So we have determined the magnitude of eta lossy and the phase shift of eta lossy, right? So always remember, always you have to keep one point in mind. So that is this phi represents what? Represents time phase shift. Time phase shift between what? Between E and H fields. Between E and H fields. E and H fields of an electromagnetic wave in a lossy medium. Okay. Okay. So I hope these points are crystal clear here, right? Okay. Right. So now see here. See, why the medium, here we will see why the medium is behaving as lossy whenever conductivity of the medium is not equivalent to 0. Okay, that's what we are going to see now. So I said that if conductivity is not equal to 0, then the medium is going to behave as what? Then the medium is behaving as lossy. So why? Why it is behaving as lossy when conductivity not equal to 0? That's what we are going to see now. See, if conductivity is not equal to 0, which means that medium is not a perfect dielectric medium, right? So which means that medium is going to have some free charge carriers, right? Conductivity not equal to 0 means what here? In any medium, conductivity not equal to 0 means there exists some free charge carriers in that medium. That's what you have to understand, right? Okay. So if conductivity is not equal to 0 means there exists some free charge carriers in this medium. Free charge carriers in this medium, right? Okay. So whenever there exists a free charge carriers in a medium, then what will happen here? So as the electromagnetic wave propagates in this medium, okay, so you are going to have oscillating electric and magnetic fields. You are going to have oscillating electric and magnetic fields. Whenever the wave is propagating in this medium, you are going to have oscillating electric and magnetic fields. And because of this oscillating electric fields here, what happens to this free charge carriers here? See, we know that whenever you are having free charge carriers, right, in a medium, and if you are having some oscillating electric field in this medium, as the wave propagates in this medium, you are going to have oscillating electric as well as oscillating magnetic fields. So this oscillating electric field is going to exert some force on this free charge carriers. Yes or no? Electric field is going to exert some electrical force on this free charge carriers. So whenever this oscillating electric field exerts some force on this free charge carriers, then this free charge carriers will start moving in the medium. Understood? So the movement of the free charge carriers within a conducting medium results in what? Results in conduction currents. Results in what? Conduction currents. Okay, so that means here IC will start flowing within this medium. So what is causing this IC here? The oscillating electric fields of an electromagnetic wave that is propagating in a medium whose conductivity is not equal to 0. So if you are having some free charge carriers, then this oscillating electric fields are going to exert the electrical force on these free charge carriers, and thus these free charge carriers will start moving in this medium. So if the free charge carrier starts moving in a medium, that is going to result in what? Conduction currents, that we call it as conduction currents. Yes or no? Okay, so this conduction currents will start flowing within the medium, right? Okay, so what happens once the conduction currents will start flowing here? What happens here is this medium is not only having the conducting nature, but also it is also having what? It is also having dielectric nature. See here, the conductivity is not equal to 0, but I am not saying that conductivity is equal to infinity. Conductivity is not equal to infinity. I am considering conductivity not equal to infinity, which means it is having some finite conductivity, right? The medium is having some finite conductivity, right? So it is not a perfect conducting medium. At the same time, it is not a perfect dielectric medium. So which means in this medium you are having both conducting nature as well as what? Dielectric nature. So because of the conducting nature, there results what? Conduction currents, right? Okay, next this medium is also going to have what? This medium is also going to have some dielectric nature. It is having dielectric nature also. Okay, it is having conducting nature plus what? Plus dielectric nature. So because of this conducting nature, it results in conduction currents. So because of this dielectric nature, what will happen? We will see. See, if you consider a conducting wire like this, and here if you consider a resistor, right? Resistor, and here if suppose the currents are flowing through this conductor, so which we call as conduction currents. So whenever this current flows through the resistor, what will happen here? Some heat is going to get dissipated across the resistor. Okay, some power is going to dissipated across the resistor. That power dissipation is nothing but what? I square R. So which is in the form of what? Which is in the form of heat, right? So here what this R is doing here? This R is providing some dielectric nature for this medium. Yes or no? It is going to provide, it will try to restrict the flow of what? The flow of conduction currents. So that means it will try to oppose the flow of conduction currents, which means it is going to provide some dielectric nature for this flow of conduction currents, right? Okay, so that dielectric nature provided by the resistance, because of this what will happen? It is going to oppose this flow of current, and thus what will happen? There will be a power loss across the resistor, which is in the form of what? In the form of heat. Okay, so here this R is providing some dielectric nature, right? So similarly here, whenever you are having an electromagnetic wave that is propagating in this medium, okay, if the medium is having conducting nature, because of this conduction currents will start flowing in that medium, and this medium is also having what? Some dielectric nature. So this dielectric nature is going to provide what? It is going to provide the resistance to the flow of what? Resistance to the flow of conduction currents. Yes or no? So this dielectric nature will try to oppose the flow of what? Conduction currents, which means it is offering the resistance, that is opposition to the flow of what? To the flow of this conduction currents. So whenever it offers some opposition to the flow of conduction currents, there will be a power loss within the medium, which is in the form of what? I square R. Okay, so this power loss will be in the form of what? This power loss will be in the form of heat. Okay, so which means whenever the medium is having both conducting nature as well as dielectric nature, so because of the conducting nature of the medium, whenever the wave is propagating in this medium, because of the oscillating electric fields, it is going to produce the conduction currents in the medium. And since this medium is also having some dielectric nature, that dielectric nature of the medium is going to provide some resistance to the flow of this conduction currents. So whenever you are having some resistance to the flow of conduction currents, there will be a power loss within the medium, which is in the form of what? Heat. Okay, so this losses we can also called as I square R losses. Okay, which is in the form of heat. So which means as the wave propagates in this medium, a part of the power or a part of the energy is going to dissipate within the medium in the form of what? In the form of heat. So that means as the wave propagates in this medium, a part of the energy or a part of the power will get dissipated to the medium in the form of heat. So it is losing some power. Okay, so what happens as the wave propagates in this medium? The amplitude of the wave is going to decay gradually because it is losing its power as it propagates in this medium. Okay, it is losing the power in the form of what? In the form of heat. Right? Okay. Okay. So I hope this point is clear here. Right? Okay. I hope this point is crystal clear. So why we are going to have the losses whenever the conductivity is not equivalent to 0. So as the wave propagates in this medium, okay, what happens? Its amplitude gradually decays as it propagates in this medium. Why means there will be some power loss. There will be some power loss within the medium itself in the form of what? In the form of heat. In the form of heat. Okay, so this power loss is nothing but what? This is because of this conduction currents, right? IC square into R, right? So if the medium is not having any conducting nature, if sigma is equal to 0, then in that case IC will become equivalent to 0. If IC becomes 0, there will be no power loss within the medium. Okay, in that case the wave is not going to get attenuated within the medium. Right? Okay. Okay. So because of the conducting nature that is present in the medium, you are going to lose some power within the medium itself. So that's why as the wave propagates in this type of medium, the amplitude of the wave is going to decay exponentially. Right. So in this case, how we can represent the expressions for electric field here? So the expression for electric field will be E into e power minus alpha z. I am writing only magnitude. Okay. So E into e power minus alpha z into what? E power j of omega t minus beta z. In this manner we can represent. Right. Okay. The amplitude is going to decay exponentially. So here alpha is not equal to what? Alpha is not equal to 0. Right. Similarly, you can write the expressions for H field that is in complex form, and also we can write in real time also. Okay, I have already told how to write the expressions for electric field and magnetic field in complex form and in real time form. Okay. Okay. So I hope these points are crystal clear here. Right. Okay. Now. Now, our medium is having both conducting nature as well as what? As well as dielectric nature. As well as dielectric nature. Right. So here we have considered the medium as what? The medium as lossy medium. Right. Okay. So because of this conducting nature of the medium. Okay, because of this conducting nature, what are the currents that are possible here? The currents that are possible are nothing but conduction currents, right? Okay, so because of the dielectric nature of the medium, what are the currents that are associated with the dielectric nature of the medium? That is nothing but displacement currents. Yes or no? So in this medium, as the wave propagates in this medium, right, you are going to see conduction currents in the medium, and also you are going to have displacement currents within the medium, because this medium is having both conducting nature as well as dielectric nature. Because of the conducting nature, IC will flow, and because of the dielectric nature, it results in the displacement currents also. Okay, you are going to have both IC as well as what? IC as well as IT, right? Okay. Okay. So now see here. Now if I compare, now I am comparing this conduction current with respect to displacement current here. So if you compare this current with respect to this current, then you can tell which nature of the medium is dominating. Yes or no? Okay, in a medium you are having both conducting nature as well as dielectric nature. So these are the currents that are associated with the conducting nature, and these are the currents that are associated with the dielectric nature. If conducting nature is dominating, then IC will be very much higher when compared to ID. Similarly, if the dielectric nature of the medium is dominating, then ID is going to be very much higher when compared to IC. So by comparing the conduction currents and displacement currents within a medium, we can judge which nature of the medium is dominating. Okay, so if at all conducting nature of the medium is dominating, then IC will be far greater than ID. If the dielectric nature of the medium is dominating, then ID will be far greater than IC. Understood? So we can check for two extreme cases. Okay, so if IC is far greater than ID, we call that medium as what? Good conducting medium, because the conducting nature of the medium is dominating there, right? Similarly, if ID is far greater than IC, then we can call that medium as a good dielectric medium, because the dielectric nature of the medium is dominating. So by comparing IC with respect to ID, we can judge the nature of the medium. Okay, that is whether whether it is behaving as a good conducting medium or it is behaving as a good dielectric medium. Okay, so for that what we are doing here is instead of comparing IC and ID, I can compare conduction current density. So IC is because of what? IC is because of JC, and this ID is because of what? Is because of ZD. If IC is present means JC is present, ID is present means JD is present. So just I am considering the conduction current density and displacement current density. So if I take the ratio of these two here, I am taking only magnitudes of JC bar and magnitude of what? Magnitude of ZD bar, right? So if you take the ratio of JC bar to ZD bar, what you are going to get, tell me? So this is equivalent to, you know that JC bar is nothing but sigma into E bar. So divided by, so what is this ZD bar here? ZD bar is nothing but dou D bar by dou T, right? Okay, see here, we know that here D bar, I can write it as what? Epsilon into what? Epsilon into E bar. So E bar is a function of what? Both space as well as time. So I can write this as epsilon into E bar of S. So that is, it is a function of space, and also it is a function of what? Time, right? So the fields are always what? Time harmonic in nature. So with respect to time, how they are going to vary? E power j omega t. Okay, now if I do dou D bar by dou TR, so then what you are going to get, tell me? So epsilon is constant with respect to time. Here E bar is a function of what? Here we have written the function of space. So this is also going to be constant with respect to time. So I can write epsilon into E bar of S multiplied by what? Differentiation of e power j omega t. So that is nothing but here I can write j omega into what? Into e power j omega t. J omega into e power j omega t, right? Okay, so if you observe this epsilon into E bar of S into e power j omega t is nothing but what? Is nothing but D bar, right? Okay, so that means if you compare this LHS side and RHS side, okay, what we can do, what is the only change? Wherever you are having dou by dou t here, there if you replace with j omega, then you are going to get the same expression or not? Yes or no? Yeah. So this total thing is nothing but D bar only. So extra what you are getting here? J omega. If you compare LHS to RHS, so in place of dou by dou t, here what you are having? J omega. So that means whenever you are differentiating a time harmonic field, then wherever you are having dou by dou t, there you can replace with what? J omega. This is for only time harmonic fields, and don't worry about that, because throughout our subject we are going to deal with time harmonic fields only. So blindly in our subject, wherever you see dou by dou t, there you can replace with what? J omega, right? Okay. So dou by dou t you can replace with what? J omega. So that is equivalent to, what you are going to get? Sigma into E bar magnitude divided by, so wherever you are having dou by dou t, there you can replace with what? J omega. So J omega d bar is nothing but epsilon into what? Epsilon into E bar. So if you take the magnitude of numerator, what you are going to get? You are going to get sigma into E divided by magnitude of denominator is nothing but omega epsilon into E. So here this E will get cancelled. You are going to get what? Sigma by omega epsilon, right? Okay, so that means if we know the ratio of sigma by omega epsilon, okay, then we can judge the nature of what? The nature of the medium. Yes or no, yaar? Okay, sigma by omega epsilon ratio is nothing but what? We have compared the conduction current density with respect to what? Displacement current density, right? So by comparing these two, we got this ratio as a sigma by omega epsilon. So magnitude of JC bar to magnitude of ZD bar is equivalent to what? Is equivalent to sigma by omega epsilon. Right? Now based on this ratio, we can judge which nature of the medium is dominating, right? Okay. So okay. So we have considered a lossy medium. Okay. So from this lossy medium, we have taken two extremes here. One is what? One is a good conducting medium, and another extreme is nothing but what? Another extreme we have considered as good dielectric medium. Okay. In generally, we have considered the general case, that is lossy medium. So in this lossy medium, if we go to one extreme, that means if the conduction currents are dominating in the medium, then we can treat that medium as good conducting medium. Similarly, if the dielectric nature of the medium is dominating, then we can call it as good dielectric medium. So these are the two extremes of this lossy medium. Yes or no? So when we can say this medium as a good conducting medium here. So whenever this sigma by omega epsilon ratio, that is JC by ZD, is far greater than 1. So that means if it is far greater than 1 means what here? JC is very much higher when compared to what? ZD. Yes or no? In that case, we can treat the medium as what? Good conducting medium. So similarly, if sigma by omega epsilon ratio, so that means if ZD is dominating, very much dominating when compared to JC, then this ratio will become what? Far less than 1. So under that condition, that means if sigma by omega epsilon ratio is far less than 1, then it is going to behave as what? Good dielectric medium. Okay, if sigma by omega epsilon ratio is neither far greater than 1 nor far less than 1, then in that case we can treat simply the medium as what? Lossy medium, which means it is having both dielectric nature as well as conducting nature. Understood? Okay, we cannot neglect any one of the natures. Right, in this case. Okay, here we can neglect the dielectric nature and we can treat it as good conducting medium, and here we can neglect the effects of conducting nature and we can treat it as a good dielectric medium. Okay. So here JC is what? JC is far greater than ZD, and here JC is far less than what? Far less than ZD. Right? Okay. So these are the general condition in order to treat the medium as good conducting medium and good dielectric medium and lossy medium, right? Okay, but we have to follow some convention. So far greater than means how much greater? When we can treat, if suppose some persons may take if sigma by omega epsilon ratio is greater than, if it is greater than 100, then they may treat it as what? then they may treat this ratio as far greater than 1. And some persons may take if sigma by omega epsilon ratio is greater than 50, then they can consider or they can treat this sigma by omega epsilon as far greater than 1. Okay, so like that anybody can take any condition here. Anybody can take any condition, but we have to follow some convention here. We have to follow some convention. Okay, so when we can treat this sigma by omega epsilon ratio, when we can treat the medium as good conducting medium means if conduction current density is 10 times greater than that of, if conduction current density is 10 times greater than that of displacement current density, then we can treat that medium as what here, good conducting medium. So this is by default here. By default, if they have not mentioned anything, okay, if they have not given any clue, okay, or if they have not given any condition when to treat the medium as good conducting medium and when to treat the medium as good dielectric medium, then in that case by default we are going to consider the ratio of what, sigma by omega epsilon. So if that ratio is greater than or equal to 10, okay, which means conduction current density is 10 times greater than or equal to that of what, displacement current density. In that case we can treat the medium as what, we can treat the medium as a good conducting medium, right? Okay, so this is by default here. By default we are going to follow this convention. Okay, that is if sigma by omega epsilon ratio is greater than or equal to 10, then in that case we are going to treat the medium as what, good conducting medium. And similarly here, if displacement current density is 10 times greater than that of conduction current density, or I can say if conduction current density is 10 times lesser than that of what, displacement current density, then we can treat that medium as what here, good dielectric medium. So here if sigma by omega epsilon ratio is less than or equal to what, less than or equal to 0.1. Okay, so which means conduction current density is 10 times lesser than that of what, displacement current density. In that case we can treat that medium as what here, good conducting medium. So this is the general condition that we are going to follow here. This is in general. This is in general. In general. In general, by default we consider these conditions. We consider these conditions. Okay, in general by default we are going to consider this as the conditions for good conducting medium and good dielectric medium. Okay, but in some books they may change this condition here, like if sigma by omega epsilon ratio is greater than or equal to 100, then they may treat that medium as good conducting medium. And in some books if sigma by omega epsilon ratio is greater than or equal to 50, then they may treat that medium as good conducting medium. So there is no wrong in that, right? Okay, but we have to follow some convention. So in general most of the books are going to follow this convention, so we are also going to follow this convention in general. Okay, but in the problems here, in the problems, whenever they are giving the problems, if they have given the condition like if in this medium, if sigma by omega epsilon ratio is greater than or equal to 20, then only treat the medium as a good conducting medium. So if they have given the statement like this, then you have to take this as the condition for the good conducting medium. Then in that case you should not take this as the condition for good conducting medium. So if they have given the condition particularly, then you have to take that condition here, right? Suppose if they have not mentioned any conditions like this, in generally they won't mention here, in general. Okay, so generally they won't mention. So under that condition, under that case we'll take these conventions by default. Understood? If they have not given any conditions regarding sigma by omega epsilon ratio, then we take this as the conditions for good conducting medium and good dielectric medium, right? Okay, okay. So when we can treat the medium as a simply lossy medium here. So here if sigma by omega epsilon ratio, that means lossy medium means it is going to have both conducting nature as well as what, dielectric nature. Okay, so none of the natures are dominating here, right? So in that case we cannot say that conduction currents are dominating, nor we cannot say that displacement currents are dominating. So this sigma by omega epsilon ratio is going to lie between what? It is going to lie between 0.1 and 10. If it lies between 0.1 and 10, then we can simply call that medium as what here? Simply lossy medium. So the two extremes of this lossy medium is nothing but good conducting medium and good dielectric medium. Okay, so what is causing the losses in this medium here? That is the conduction currents are causing the losses. So if the conduction currents are more in the medium, so it is going to behave as what? High lossy medium. So that's why this medium is also called as what here? This medium is also called as, we can call it as high lossy medium. High lossy medium. So good conducting medium or high lossy medium. And in this medium, the conduction currents are less. If the conduction currents are less, then the losses are also going to be less, because the losses are in the form of what? IC square R. Yes or no? So if conduction currents are less, these IC values are also going to be less, which means the power lost within the medium is also going to be less. Okay, so which means it is going to behave as what? Low lossy medium, or you can say simply high lossy dielectric. They will use generally this terminology, that is high lossy dielectric. They will call it as high lossy dielectric. Okay, and here we can say it as a low lossy dielectric. Low lossy dielectric medium. Okay. So in your dielectric medium, when you are going to have high losses here, when you are going to have high losses, you are going to have high losses if the conducting nature of that medium is dominating. Okay, and when you are going to have the low losses in your dielectric medium, so when you are going to have the low losses means whenever the conduction currents are lesser in that medium when compared to displacement currents. Okay, in that case you are going to have low losses. So that's why we can call this medium also as a low lossy dielectric, and this medium as a simply high lossy dielectric. And simply this medium we can simply call it as sometimes they will call it as a lossy dielectric. Simply they will call it as lossy dielectric. Okay, okay. So we are expressing these losses with respect to this dielectric nature of the medium, right? Okay, okay. So lossy dielectric means if the medium is having some finite conductivity, then you are going to have some losses in that medium, right? So if the conduction currents are more, you are going to have high losses in that medium. If the conduction currents are less, you are going to have less losses in that medium. Okay, so whenever it is having less losses, the medium, in this medium, the displacement currents are dominating over the conduction currents, which means the dielectric nature is dominating over the conducting nature, and hence we can call it as good dielectric medium. Whereas here the conduction currents are dominating over the displacement currents, so that's why we call it as what? Good conducting medium, right? Okay, okay. So generally this is the conditions we are going to consider for good conducting medium, and this is the condition for good dielectric medium by default. Okay, if they are not given any condition, you are going to consider this as the conditions for good conducting and good dielectric. Okay, okay. So here you are having lossy dielectric. I am giving just a summary here. This is very, very important here. This is very, very important. What is the condition for lossy dielectric? Sigma by omega epsilon ratio is going to lie between what? 0.1. This is by default conditions here. These are not compulsory conditions. Okay, if they have not mentioned any condition, then we are going to assume this as the conditions, right? So sigma by omega epsilon ratio is going to lie between 0.1 and what? 0.1 and 10. So we can go to one extreme of this lossy dielectric, which is called as high lossy dielectric, or we can call it as good conducting medium. Okay, so in this case sigma by omega epsilon ratio, if it is greater than or equal to 10, then we can treat that medium as good conducting medium or high lossy dielectric medium. So another extreme of this lossy dielectric is nothing but what? Low lossy dielectric medium, or we can call it as what? Or we can call it as good dielectric medium. So in this case What is sigma by omega epsilon ratio here? Tell me. What is sigma by omega epsilon ratio? Tell me. So sigma by omega epsilon ratio, what you are going to get? You are going to get if it is less than or equal to what? Less than or equal to 0.1. Okay. Okay. So in general, if the medium is having conductivity not equal to 0, then it is going to behave as a lossy dielectric. So the condition for lossy dielectric is in general if sigma by omega epsilon ratio lies between 0.1 to 10. So in this we can go to two extremes, one is high lossy and another one is low lossy. The condition for high lossy is nothing but sigma by omega epsilon greater than or equal to 10. So here conduction currents are dominating over displacement currents, and for good dielectric medium or low lossy dielectric medium, sigma by omega epsilon ratio must be less than or equal to 0.1. Understood? Okay. Here conduction currents are 10 times greater than that of displacement currents, whereas here the conduction currents are 10 times lesser than that of what? 10 times lesser than that of displacement currents. Right? Okay. Okay. So that's what you have to understand from this lossy medium here, from this lossy medium, right? Okay. So now see here. Now see here, if you consider good conducting medium here, if you consider good conducting medium, so that means here we are assuming sigma by omega epsilon ratio is far greater than 1, which means by default we are going to consider the condition as sigma by omega epsilon is greater than or equal to 10. Okay, so this is the condition for good conducting medium, right? Okay. So now for good conducting medium we try to write the expressions for what? The expressions for gamma, okay, alpha, beta, and then we try to write the expression for intrinsic impedance and all those things, right? Okay. Okay, just we are going to impose this condition, in case of what? Lossy dielectric. See, from the lossy dielectric only we are getting these two extremes. One is high lossy dielectric. This is also called as what? This is also called as high lossy dielectric medium. High lossy dielectric medium. Okay. 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 So from the expressions of a lossy dielectric, by imposing these conditions, we are going to get the expressions for a high lossy dielectric, right? Okay. Okay. So in case of high lossy dielectric, what is the condition? Jc is far greater than what? Jc is far greater than Zd, right? Okay. Okay. Right. And we are having one more name here for this sigma by omega epsilon ratio. So that is this sigma by omega epsilon ratio is also called as what? Is also called as loss tangent here. There is another name for this sigma by omega epsilon ratio, which is also called as loss tangent. Why we are calling it as loss tangent here? Because see here, we know that Jc bar is equivalent to sigma into E bar, whereas Zd bar is equivalent to what? Is equivalent to, I can write Zd bar as what? Zd bar as a j omega epsilon into what? Epsilon into E bar. Yes or no? Zd bar is equivalent to j omega epsilon into E bar, right? Okay. So actually Zd bar is dou d bar by dou t. Wherever you are having dou by dou t, there you can replace with j omega, and d bar I have replaced with epsilon into E bar. Now if you observe these two expressions here, okay, what is the time phase shift? What is the time phase shift between this Jc bar and Zd bar here? What is the time phase shift between Jc bar and Zd bar? Tell me. So here you are having sigma into E bar. Here you are having what? J into omega epsilon E bar. So that means the phase shift between Jc bar and Zd bar is how much? 90 degrees. Okay. So the time phase shift, between what? Time phase shift between Jc bar and Zd bar is how much here? Is 90 degrees. Is 90 degrees. Now if I try to form a diagram, okay, for Jc and Zd. So if I consider this as Jc here, sorry, if I consider this as what? If I consider this as JC, right? Okay, so the angle between JC and ZD must be what? Must be 90 degrees. So this is JC and here you are having ZD. Let us say this is ZD. So the time phase shift between this JC and ZD must be what? Must be 90 degrees. So with this I can form what? I can form a right angle triangle like this. I can form a right angle triangle like this, right? Okay, so here this angle I am representing it with a delta, right? Now if I take a tan delta here from this right angle triangle, if I take tan delta, that is opposite side by adjacent side, which is equivalent to JC by what? JC by ZD, which is equivalent to what? Sigma by omega epsilon, right? So we are expressing this sigma by omega epsilon ratio in terms of what? In terms of tan function, in terms of tan function. See what happens if the sigma by omega epsilon ratio increases here? This tan function value is also going to increase or not? Yes or no here? So as sigma by omega epsilon ratio goes on increases, this tan function will also going to increase. So what do you mean by sigma by omega epsilon ratio increasing? It means the losses in the medium are increasing, right? So that means as the tan function value goes on increases, the losses in the medium are also increasing. So which means we are expressing the losses in terms of what? Tan function. So that's why this tan delta, which is nothing but sigma by omega epsilon ratio, is also called as what? Is also called as loss tangent. Is also called as loss tangent. So if this loss tangent value is more, means sigma by omega epsilon ratio is more, which means the losses in the medium are more, right? Okay, so that's why, and we are expressing those losses in terms of what? Tan function. So that's why we call it as what? Loss tangent. Okay, if this ratio is small, then this tan function value is also going to decrease. So if this tan function value is lesser, means the loss tangent value is also going to be lesser. Loss tangent value lesser means in that medium the losses are going to be very less. That's what you have to understand, right? Okay, okay. So now here one more point I want to specify here is here we are representing this loss tangent as what? Tan delta, tan delta. Okay, so while going to the topic of skin depth here, while going to the topic of skin depth, there also the skin depth we are going to represent in terms of what? In terms of delta only. Skin depth will represent as what? Delta, with the symbol delta. Okay, but this delta is different, and here whatever the delta that you are representing, this delta is different. Okay, the units of this this delta is nothing but the angle here, the angle that you are measuring here, right? So this delta is completely different, and skin depth delta, whatever you are representing here, the skin depth delta is completely different. So don't confuse between these two, right? Okay, or in order to avoid the confusion, if you want, you can represent, instead of delta, you can represent it as theta also, no problem, since it is an simply angle, right? Okay, okay. But in most of the books they are representing with tan delta only. So that's why I have also represented in terms of delta, right? Okay, you can use theta or you can use phi. Okay, whatever you want you can use here for this angle, right? But you have to keep in mind that this tan delta represents what? Loss tangent. So this delta is different, and this delta is different. Okay, so these things you have to keep in mind, right? Okay, so okay, right. So we try to get the expressions in case of what? In case of good conducting medium, right? Okay, so now see here gamma here, gamma for lossy medium, what we got? Gamma for lossy dielectric, we got it as what? Square root of j omega mu into sigma plus what? J omega epsilon, right? Okay, okay. So here sigma by omega epsilon ratio far greater than 1 means sigma is far greater than what? Far greater than omega epsilon. Far greater than omega epsilon. Right? Okay. So in case of good conducting medium, so in case of good conducting medium, okay, so sigma will be far greater than what? Omega epsilon. So if sigma is far greater than omega epsilon here, if you compare this sigma with respect to omega epsilon, this sigma value is far greater than what? Far greater than this omega epsilon. So which means we can neglect this omega epsilon term when compared to sigma. Okay, so by neglecting this omega epsilon term, by comparing with respect to sigma, okay, by comparing with respect to sigma, you are going to get what? You are going to get the propagation constant for what? For good conducting medium. So in case of good conducting medium, we can neglect this omega epsilon term when compared to this sigma. So if you neglect this term here, if you neglect this term, what you are going to get? You are going to get simply square root of what? J omega mu into what? Into sigma. J omega mu into sigma. Okay, so this is equivalent to, so here I can write this as a square root of what? Square root of J omega mu, square root of omega mu sigma. This is the magnitude. What is the phase shift here? J means the phase shift is 90 degrees. If you take it out of the root, you have to divide that angle by 2. So 90 by 2 is nothing but 45. So the phase shift is nothing but 45 degrees. Right. So this 45 degrees, if I write, I can write this 45 degrees as what here? E power j 45 degrees. In this manner I can represent, right, in polar form. Right? Okay. So e power j 45 means what here? Means cos 45 plus j sin 45. So that is cos 45 is 1 by root 2 plus j sin 45 means j into 1 by root 2. So I have expressed this in rectangular form in this manner. Okay. Now finally, what you are going to get? The propagation constant for good conducting medium. See, generally in books, they won't mention this suffixes here. Okay, they will simply mention gamma, that's it. Whether it is lossy medium or lossless medium, they won't mind. They will simply represent simply gamma, right? Okay, but you have to understand, depending upon these expressions and all these things, we have to understand that gamma is related to which medium, right? Okay, okay. So in order to make you understand, here I am writing everywhere these suffixes, right? Okay, so that you don't have any confusion while understanding these things here, right? So gamma for good conducting medium is equivalent to what? So if you multiply this one with this one, you are going to get the real part as omega mu sigma by 2 plus imaginary part also you are going to get the same expression, that is omega mu sigma by 2. So the real part of gamma is called as what? Is called as alpha, right? Okay, so this is alpha for a good conducting medium, and this is beta. The imaginary part is nothing but what? Is nothing but beta. Okay, so the imaginary part is nothing but beta for good conducting medium. So in case of good conducting medium, the alpha value and beta value, or the expressions for alpha and beta, both are what? Both are same. So they are different in terms of units, but mathematically, expression wise, both are going to be same in case of good conducting medium. So alpha for good conducting medium is equivalent to what? Square root of omega mu sigma by 2 Nepper per meter, and beta for good conducting medium, beta for good conducting medium is equivalent to what? Is equivalent to square root of omega mu sigma by 2 radian per meter. So these are the expressions for alpha and beta in case of what? In case of good conducting medium, right? Okay, okay. Now if you observe one thing here, in case of good conducting medium, see, now we have entered into good conducting medium. Okay, keep this point in mind, right? So in a good conducting medium, we got the expression for alpha, this one, and we got the expression for beta, this one. Whereas this alpha and beta expressions are different if you consider lossy dielectric. Okay, there we got different expressions. Here we are getting different expressions. Yes or no? So by imposing the conditions for a good conducting medium, we are getting these expressions for alpha and beta. Okay, if you observe this expression for alpha here, if you observe this expression for alpha, what we can conclude in case of good conducting medium is here mu is constant, sigma is constant, 2 is also constant. This omega, I can write it as what? I can write it as 2 pi into f. So this 2 pi is also constant. Okay, only the frequency is variable. So that means I can say in a good conducting medium, alpha is proportional to what? Square root of frequency. So that means the attenuation constant in case of a good conducting medium, it is not true for all the cases here. It is not true for lossy dielectric, and it is not true for good dielectric medium. It is true only for good conducting medium. You have to keep that point in mind. Okay, so as the medium properties changes, okay, the expressions for alpha, beta, eta, all those things are also going to change, because these parameters are going to depend upon medium characteristics, right? Okay, okay. So this attenuation constant is depending upon what here? It is depending upon frequency. That means it is directly proportional to frequency. So that means if the wave is propagating in a good conducting medium, specify this point, I am specifying this point, okay, good conducting medium. If the wave is propagating in a good conducting medium, then the attenuation constant is proportional to square root of frequency, which means as the frequency increases in a good conducting medium, then the attenuation constant in that medium is also going to increase. Okay, which means if the wave is propagating in a good conducting medium, you have to prefer always low frequency signals in order to have less attenuation. Yes or no here? Okay, if you are sending the signals through a good conducting medium, how you have decided that it is a good conducting medium? You have determined sigma by omega epsilon ratio and you got it as greater than or equal to 10. So that's how you have fixed that it has good conducting medium. Okay, so in that good conducting medium, so as the frequency of the wave changes, its attenuation constant is also changing. So here, as the frequency increases, the attenuation constant is also increasing, which means high frequency signals are going to propagate to a lesser distances in case of what? Good conducting medium, because high frequency signals are going to suffer very high losses in case of what? Good conducting medium. So that's why whenever you are sending the signals through a good conducting medium, you have to prefer always what? You have to prefer always low frequency signals, right? Okay, so you have to keep this point in mind, right? Okay, this is very important here. This is very important, right? Okay, okay. Next, next. Okay, this is a beta for a good conducting medium. Next, what is intrinsic impedance here? What is intrinsic impedance for a good conducting medium? So we can derive this from lossy dielectric itself, right? Okay, so if we consider eta for lossy, what we got? We got square root of what? J omega mu by sigma plus j omega epsilon. So in case of good conducting medium, sigma is far greater than what? Omega epsilon. So here you are having sigma and here you are having omega epsilon. So if you neglect this omega epsilon term when compared to sigma, you will get the expression for what? Good conducting. You will get the expression for intrinsic impedance for good conducting medium, right? So for good conducting medium, what is the expression you are going to get? That is equivalent to square root of what? Square root of j omega mu by sigma. So the eta, we know that eta is the ratio of what? E field to H field, right? Okay, okay. So in a good conducting medium, E by H ratio is equivalent to what? So what is the magnitude here? Magnitude is nothing but square root of omega mu by sigma. What is the phase shift? So J means 90 degrees. If you take it out of the root, you have to divide that angle by 2. So you are going to get the phase shift as what? 45 degrees. 45 degrees. Okay, so which means the time phase shift between electric field and magnetic field. The time phase shift between electric field and magnetic field in case of what? In case of good conducting medium is how much here? It is 45 degrees. Whereas in case of lossy medium, what is the time phase shift we got? Phi lossy is equivalent to what? Is equivalent to 45 degrees minus tan inverse of what? Minus tan inverse of omega epsilon by sigma. Okay, so sigma by omega epsilon ratio is far greater than 1 in case of good conducting medium, which means omega epsilon by sigma, reverse of this one, will be what? Far less than 1. So that means this ratio, if it approaches to 0, it is approaching to 0 in case of good conducting medium. So if it approaches to 0, okay, then tan inverse of 0 will be approximately what? Will be approximately goes to what? Will be approximately go to 0. Then in that case, you are going to get what? 45 degrees. So that's what we are getting here in case of good conducting medium. Here we have made this is approximate results here. Yes or no? Because we have made these approximations. We have neglected completely this term when compared to sigma. Understood? Okay. So because of this, we got the expression as here the phase shift as 45 degrees. So this is the approximate phase shift between electric field and magnetic field in case of good conducting medium, right? Okay. So here they may ask you a direct question like what is the time phase shift between electric field and magnetic field in case of good conducting medium? The answer is nothing but 45 degrees. So this is the time phase shift. This is the time phase shift between what? Between E and H fields. Between E and H fields in a good conducting medium. And if you observe here, okay, E by H ratio is equal to magnitude and phase shift. So here we can say that the electric field is leading magnetic field by how much here? Plus 45. Yes or no? So we can say that in a good conducting medium, electric field leads H field. Electric field leads H field by what? By 45 degrees. Or I can say the same thing in another manner also. That is, I can say H field lags E field by 45 degrees. Or I can say the same thing in another manner, that is H field leads E field by minus 45 degrees. Okay, H field leads E field by minus 45 degrees or H field lags E field by 45 degrees. Both mean what? Both mean same only. Okay, it is just a terminology here, that's it. Okay, we can say the same thing in different manner like this. Okay. So the electric field in a good conducting medium leads magnetic field by 45 degrees, or you can say it as H field lags E field by 45 degrees, or you can say it as H field leads electric field by minus 45 degrees. So in this manner also you can tell. Okay. Right. Okay. Sir, is the syllabus same for Vishal Ram? Is the syllabus same for IN? No. For IN it is completely different here. For electrical and instrumentation students, I will take one more session for them separately. Right. This is exclusively for EC students. Right. Okay. Next is Biswas. For a purely imaginary angle is 90 degrees, isn't it? See, which one you are taking? Yes, for J it is 90 degrees, but that 90 degrees is under root now. So if you take that angle out of the root, you have to divide that angle by 2. Yes or no? Okay, so if you are having square root of some angle phi, if you take this angle phi out of the root, then you have to divide this angle by what? By 2. I hope you know this thing, right? Okay. Right here. So I hope your doubt is cleared. Biswas. Right here. So we got the expressions for alpha, beta, and also we have seen the expression for eta in case of what? Good conducting medium. Right? Okay. So next we will see the expression for phase velocity in case of what? In case of good conducting medium. Phase velocity in case of good conducting medium. See, I have already told the phase velocity we can determine as the ratio of what? Omega by beta. But here we are dealing with a good conducting medium, so you have to take the ratio of omega by beta. So whereas beta you have to consider for good conducting medium. Okay, so this is equivalent to omega by, so what is beta for a good conducting medium? Just now we have determined here. So beta for good conducting medium is nothing but what? Is nothing but a square root of omega mu sigma by 2. So the values of alpha and beta, the expressions for alpha and beta are same in case of what? Good conducting medium. Right? Okay. Okay. So omega by beta for good conducting medium. So for good conducting medium, beta value is nothing but square root of omega mu sigma divided by what? Divided by 2. Okay. So if you do this, what you are going to get? You are going to get square root of what? Square root of 2 omega by mu sigma. Square root of 2 omega by mu sigma. Right? Yes. So this is the phase velocity you are going to get in case of a good conducting medium. In case of good conducting medium, we get the phase velocity as a square root of 2 omega by mu sigma meters per second. Meters per second. Right? Okay. Right. So if you consider in a lossless medium here, if you consider in a lossless medium, if you consider the phase velocity, what is the phase velocity in case of lossless medium? What is the expression? Is nothing but what? C by root over mu r epsilon r. C by root over mu r epsilon r. So here if you observe, phase velocity is equivalent to what? Omega by beta, where omega by beta is nothing but what? Omega into root over mu epsilon. So here omega will get cancelled. So finally you are going to get the expression for phase velocity independent of what? Independent of frequency. So why we are getting like this here? Because here if you observe, beta is related linearly to omega. Yes or no? So here we can say that beta is linearly related to omega. Since it is linearly related to omega, what's happening? Phase velocity is the ratio of omega by beta. Since beta is linearly related to omega, here omega and here omega is getting cancelled, and the phase velocity is becoming independent of what? Here it is becoming independent of frequency. Independent of frequency. Whereas in case of good conducting medium, I am talking about good conducting medium. In case of good conducting medium, what is beta here? What is beta? Beta is nothing but square root of omega, square root of omega mu sigma divided by what? Divided by 2. So here in this case, the phase velocity in case good conducting medium is nothing but what? Omega by beta. Omega by beta. So here if you observe here, omega by square root of what? Omega mu sigma by 2. If you observe the denominator here, okay, so here beta is not linearly varying with respect to omega. It is related non-linearly to omega. Yes or no here? Okay, if it is linear variation with respect to omega, then here omega will be cancelled, and then the phase velocity would have become independent of frequency. But here, since beta is non-linearly related to omega, in the final expression, this omega is not going to get cancelled. So in the final expression, you are going to get the phase velocity as a depending on what? Depending upon frequency. So here in this case, here beta is non-linearly related. Beta is non-linearly related to omega. Non-linearly related to omega. Okay, so in this case, the phase velocity is becoming a function of what? A function of frequency. So whenever beta is linearly related to omega, okay, in that case, the phase velocity is becoming independent of frequency. So which means if you send some information in this lossless medium, that information is going to consist of many frequency components. So all those frequency components are going to travel with the same velocity, because the phase velocity in lossless medium is independent of what? Frequency, and hence all the frequency components of that information are going to travel with what? Are going to travel with the same phase velocity. Okay, whereas if you send the information through a good conducting medium, and that information is going to have many frequency components, and here different frequency components are going to travel with what? Are going to travel with different phase velocities. So what happens if different frequency components travels with different phase velocities here? It is going to cause what? It is going to cause distortion. So why it is depending upon frequency? Because here beta is non-linearly related to what? Beta is non-linearly related to omega. That's why this phase velocity is depending on the frequency. Okay, and hence different frequency components are going to travel with different velocities, which is going to cause some distortion in that medium, right? Okay, I will explain now how that distortion is going to occur, and all those things I will explain. Okay, but as of now, see here, if beta is non-linearly related to omega, then that medium is said to be dispersive medium here. Okay, then that medium is said to be dispersive medium. So in a dispersive medium, the phase velocity will become depending upon what? Frequency, which means in a dispersive medium, different frequency components are going to travel with different velocities. Okay, so here in this medium, in lossless medium, beta is linearly related to omega. So if beta is linearly related to omega, then that medium is said to be non-dispersive medium. So in a non-dispersive medium, the phase velocity is independent of what? Frequency. So which means all the frequency components are going to travel with the same velocity. Okay, yeah. So here, what is the conclusion we can make here is if beta is proportional to omega, then we call that medium as what here? We call that medium as a non-dispersive medium. We call that medium as a non-dispersive medium. If beta is non-linearly, if beta is non-linearly related to omega, if beta is non-linearly related to omega, then that medium is said to be what? Then that medium is said to be dispersive medium. Okay, so what happens whenever beta is linearly related to omega? So here in this medium, the phase velocity becomes independent of what? Independent of frequency. So what happens if beta is non-linearly related to omega here? So here the phase velocity becomes what? Phase velocity depends. Phase velocity depends on what? Depends on frequency. It is going to depend upon frequency. Okay. So here in non-dispersive medium, all the frequency components are going to travel with the same velocity, whereas in case of In a non-dispersive medium, all the frequency components are going to travel with same phase velocity, because here the phase velocity is independent of frequency. Why it is becoming independent of frequency? Because in this medium beta is linearly related to omega, and hence the phase velocity is becoming independent of frequency. Whenever beta is non-linearly related to omega, then that medium is going to act like a dispersive medium. So in this dispersive medium, the phase velocity is going to depend upon frequency, which means different frequency components are going to travel with what? Different velocities, right? Okay. Okay. So what happens if different frequency components travels with different velocities? What happens is, if suppose on this side one singer is present, right? Okay, so let us say this channel, this is the channel. So this channel is behaving as good conducting medium, right? Okay, so on this side you are listening, the audio, right? Okay, so here the signal is transmitted through this good conducting medium. So the singer is singing like a sari gamma. So she is singing like a sari gamma. She is singing like sari gamma, right? Okay. Okay, so let us allot some frequencies to this sari gamma. So let us say this is a 1 gigahertz, and let us say it is 2 gigahertz, and let us say this is 0.5 gigahertz, and let us say this is 3 gigahertz. Let us assume here. I have allotted for each this sari gamma, I have allotted some frequency. Let us assume, okay, randomly I have allotted some frequency to this sari gamma, right? So here in a good conducting medium, the phase velocity in a good conducting medium is depending upon what? It is depending upon frequency. So here mu is constant, sigma is also constant, 2 is constant, this omega is nothing but 2 pi f, 2 pi is also constant. So Vp is proportional to what? Square root of frequency. So in a good conducting medium, the phase velocity is proportional to what? Square root of frequency, right? So that means if the frequency is more, then the phase velocity of that component is also more. Okay, so whenever he is listening on this side, first what he is going to listen here? Tell me. So the higher frequency component is going to travel faster. So here the singer is singing like sari gamma, and here you are having the listener. Here, right? Okay, so he is listening the song. So whenever this signal is transmitted through a good conducting medium, we know that in a good conducting medium the phase velocity is going to depend upon the frequency. So higher frequency components are going to travel with more velocity. So which means here first what he is going to listen. So first whenever here the singer is singing sari gamma, so ma is having the highest frequency component, so it is going to travel faster when compared to all the other components. So first he is going to listen what? Ma, right? Okay, next what he is going to listen? Next he is going to listen re, right? Next what he is going to listen? Sa, and then finally he is going to listen ga. Okay, ma, re, sa, ga, right? So in this manner he is going to listen, but actually the singer is singing like sari gamma, but here the listener is listening like mari sa ga, right? Okay, so it is a distortion or not, right? Okay, so if different frequency components travels with different velocities, this is the distortion that you are going to get, right? So it will get shuffled based on the frequency. This is going to get shuffled, and hence the information will get what? Distorted whenever you are listening on the other side, right? Okay, okay. So that's why it is going to cause what? It is going to cause a distortion. In this medium. So what happens if different frequency components travels with different velocities? So if different frequency components travels with different velocities, it is going to cause the distortion within that medium, right? Okay, so in a dispersive medium, Beta is non-linearly related to omega. So whenever beta is non-linearly related to omega, the phase velocity will become depending upon what? Frequency. So different frequency components are going to travel with different velocities, which is going to cause the distortion in that medium, right? Okay. Okay, yeah. So I hope you have understood what do you mean by dispersive medium and what do we mean by non-dispersive medium, right? Okay, so the good conducting medium is behaving as dispersive medium, whereas the lossless medium is behaving as what? Is behaving as non-dispersive medium, right? So it is based upon the relation between beta and omega. If beta is linearly related to omega, then we call that medium as non-dispersive medium. If beta is non-linearly related to omega, then we call that medium as dispersive medium. Okay. Okay, yeah. Okay, right. So I hope these things are crystal clear here, right? Okay. So next what we will do here is if you revise all these things here up till here, okay, up till here, please revise all these things. So I am going to take 2 more sessions here. If possible, I will take 2 more sessions like this. Okay, for a complete revision of EMT, I will take 2 more sessions. So whenever I take 2 more sessions, there I will discuss the remaining things. Okay. So next I am going to discuss some problems based on this sigma by omega epsilon ratio and all. Okay. So how to deal with those problems, right? Next we will see skin depth and then we will see Poynting theorem. Okay. So once you understand the basics here, basic concepts, then the subject is going to be very, very easy and simple, right? Okay. So that's why whenever I teach EMT, I will concentrate morely on the concepts. Okay. So because the student, if you are not clear with the concepts, then you cannot solve any problems in EMT. Okay. So by chance, if you get some problem, by luck you may do it correctly, but the thing is you have to know the concepts clearly, then only you can do 100% correctly in the examination, right? Okay. Okay, yeah. So with this I am ending up this lecture here. So we have started dealing with a lossy medium. In that we have studied about the good conducting medium, right? Okay, we have derived all the expressions in case of good conducting medium, right? So with this I am ending up this lecture. So in the next lecture we will see about a good dielectric medium also. See, almost the characteristics of good dielectric medium is almost similar to the lossless medium here. So there is no need to stress that much in case of good dielectric medium. You can easily understand because almost all the properties are related to what? Are almost similar to what? Are almost similar to lossless medium only. So that's why you can easily understand that good dielectric medium. So no problem in that, right? So next we will see skin depth, which is very, very simple. Next we will see the most important topic, that is Poynting theorem. That is also going to be very, very simple. Okay, the thing is nothing but you have to understand the concepts in a crystal clear manner. Then you can solve the problems very, very easily, right? Okay. 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 Funny, yes, I will plan to cover transmission lines and waveguides also. Okay. So most probably I will take the next session day after tomorrow here. Okay. So tomorrow it is not possible. So I will take day after tomorrow, and then again I will take 1 day gap, and again I will take 1 more session, right? So within 2 more sessions I will try to do this complete revision of EMT. Okay. So after completing skin depth and Poynting theorem, we will mostly complete this wave propagation in different media. Then after that I will go for transmission lines, then I will go for waveguides and antennas. Okay. So these are the topics mainly I am going to cover. Okay. After this we will cover transmission lines and After that we will cover waveguides, and after that we will cover antennas. Okay. Okay, so I briefly go through these topics also. I will revise all these topics also. Okay. Okay. And regarding that whether it becomes private, I don't know that here, so that will be taken care by the management. Okay, so maybe I am thinking like they may keep this session up to maybe up to GATE exam. Maybe after GATE exam, maybe it may not be available. I think so. I am thinking so. Okay, I am not clear whether it become private or not. So that decision will be taken by the management, right? Okay. But if you attend a live session na, then your time will be saved here. Your time will be saved. So you can learn along with me, and your time will also be saved. So if you learn along with me, then after this you are getting one more day. Tomorrow I am not taking any class. Day after tomorrow again I am taking class. So today and tomorrow you can revise all these concepts once, and you try to practice some problems. If you find any problems, you can practice those problems also. Okay, anyway I will deal with the problems also, but what I am saying is, since you have understood the concepts in a crystal clear manner, you try to solve the problems on your own also, right? Okay. Okay, right. Okay, so thank you. I hope each and everything is crystal clear. So I am ending up the session here. So we'll meet most probably day after tomorrow, so that you will get get that notification in the YouTube, right? Okay. Okay. Okay, so okay then, take care, bye bye, and thank you for watching.